just Dr. Saif will introduce you. So we'll just wait for a few minutes more because I'll let a few more people join. They are still logging in.
I understand the situations.
Yes, sir. Oh.
Let us
We may
start
start
at
at 9:40, I
9:35.
think. Okay.
9:35 we can start. I think.
Another 1 minute.
Another 1 minute.
Sir, today Indra is busy, so you have to take care of the questions also.
Okay, okay. So participants, whoever has a question, he can write, or he or she can write in the chat box, and the speaker can take it whenever he wants to. He has time or wants to take a break, or towards the end. So please don't hesitate in asking the question, because that will clear your doubts and also it will help us. It's already 9:36 in my computer. Thank you. Ambuj sir?
Yeah, I think we can start.
Okay, okay. Thank you, sir. So, good morning to all of you. And actually, we are now in the last on the last day of this school, and I hope that all the participants are enjoying this school and it is very useful for them. And actually, we are very much happy that you are here in this school. So today we are going to have first lecture by Professor Shu Seki, and myself, I am Saif. So I will be coordinating in this session. So before that, please let me introduce the speaker today. Okay, he is Professor Shu Seki from Department of Molecular Engineering, Kyoto University. He graduated from the University of Tokyo in 1991 and received Doctorate of Engineering from Osaka University in 2001. He joined Chemistry Division of at Argonne National Lab in 1995 and Delft University of Technology in 2000 as a visiting scientist. Then he started working as a professor of chemistry at the Graduate School of Engineering, Osaka University in 2008. And in 2015, he was appointed as a professor of physical chemistry at the Department of Molecular Engineering, Kyoto University. Professor Seki has published more than 500 articles in peer-reviewed journals, and he has delivered more than 100 plenary keynote invited lectures in conferences, symposium, and at IUAC. Actually, we are very happy that he chose IUAC for conducting some of his research work. So we have he has a strong collaboration at IUAC, and from his vast experience, research experience, he will be telling us about fabrication of nanoparticles today with high energy ions. So let me ask Professor Shu Seki to begin his lecture.
Thank you very much. My name is Shu Seki. I'm now talking from Kyoto University. And this is my pleasure to deliver my lectures for you. And maybe today is the last day of the schools, and maybe somebody are a bit tired. But anyway, I would like to introduce you about the recent progress of the nanomaterial fabrications by using the ion beams. And some work was done by the collaboration with IUAC as chairperson already introduced. But anyway, today I would like to mainly focusing on to the our work done within these 10 years. So let me start my talk from the very basic and fundamentals of the radiation-induced processes. Maybe everybody know that the very the beginnings of the discovery of ionizing radiation was done by the two very established scientists named Henri Becquerel and Wilhelm Röntgen. And since the initial research work on the ionizing radiation, particularly the ionizing radiation interaction with matter, always we are using in the terms of rays. And let me say that, one of the most important things is, so far, by checking the CSOLAS by the Oxford, there are clear descriptions that we should use the term of the rays as always the plural form, not a single form, because since the discovery of X-rays, it is discovered as invisible something. So invisible something cannot be counted by themselves. So we should use the term of rays always in the plural forms. However, my question is, whether it is possible to use a single form of ray. The answer is our research work introduced you subsequently. And so during the initial research work on the radiation with materials done in the beginnings of the 20th century. And, particularly not only for the inorganic materials, the organic materials also met the ionizing radiations in the initial stage of the research work in the radiations. For instance, once if we changed. And such kind of the behavior can be reflected or not by the nanostructure. This is the question. So we try to make nanostructures based on the polynippon, and very fortunately, successfully, as shown in this figure, we have realized one-dimensional nanostructures. But the very more interestingly, once after the isolation of the nanowires, and once if we're heating up the substrate, the nanowire was shrunk as shown in this view graph. And again, once if we cool down to the lower than the phase transition temperature, again the nanowire was stretched. So such kind of the morphological changes was clearly observed against a simple temperature control. And so we have successfully realized the thermal-responsive one-dimensional nanowire system based on this very well-known commercially available polymeric systems. And the other interesting feature of this kind of the one-dimensional nanowire is, it's very high feasibility to combine the two different kinds of the polymer materials into the one single nanowire forms, because the protocols of the nanowire formation is very simple. Only the requirement is to prepare the thin solid film of organic substances on the substrate. So after the preparation of the one layers onto the substrate, successively the second layer was overcoated. Again, vertically, ion beam was irradiated, passing through the double layer solid films. Eventually, along the particle trajectory, double-decker nanowires was generated. And as displayed in these four figures, clearly the double-decker nanowire was observed. And very interestingly, one part of the nanowires was thermal responsive. So against the temperature controlled, only one segment of the nanowire was shrinked and again they stretched. So this microscopic observation clearly suggests that nanowire was composed of completely two distinct polymer substances. And one of the critical issue in case of the responsive nanomaterials is their feasibility against the external stimuli. And so we also check about the thermal responsibility against the temperatures for one segment of the nanowires. And as shown in this view graph, the stretching and shrinking of the one segment of the nanowires can be confirmed again and again. And very high reliability for the morphological changes can be confirmed by these very simple experimental protocols. And for the quantitative analysis, because I'm the physical chemist, so such kind of the morphological changes can be checked by some kind of the statistical mechanical measurement. And so the sizes of the stretched form and the shrunk form of the nanowires was confirmed by the precise tracing of the structural changes on the substrate. And as given in this view graph, clearly one segment of the nanowires was rapidly respond to the external stimuli, in this case, the temperature controlling. And only one segment will be stretched or shrunk again and again. And so we can use this type of nanomaterials exactly as the external stimuli responsive nanomaterials. And as I explained in the previous slide, we have successfully realized the thermal responsive one-dimensional nanomaterials. And the morphological changes of the one-dimensional nanowires also convert the thermal energy into the kinetic energies. So one end of one segment of the nanowires, once if we stretched, they have a very huge surface areas. And in this form, the nanowire surfaces can interact with the small particles. However, once after the heating up of the materials, the nanowire should be shrunk. So the interfacial interactions with the small particles should be fixed at some certain point where nanowires was shrunk. And so, yeah, such kind of the kinetic behavior was also observed by an interaction of the nanowires to the nanoparticles. In this case, we are using the polystyrene nanoparticles. And as you know, the polystyrene is a very well-known synthetic polymer materials, and their surfaces are very strictly hydrophobic. And so the hydrophobic form of the nanowires has a high affinity to the nanoparticles. And after the interaction with the nanowire to the nanoparticles, as shown in this view graph, the clearly nanoparticles fix onto the substrate. And again, once if you cool down the substrate, the nanoparticle will be released. And next challenging task to realize the thermal stimuli responsive nanomaterial is to convert the photo energy to the kinetic energy. And this light responsive materials has been well investigated in the field of organic chemistry, and one of the most representative chemical unit where the which show the very high responsibility responsive properties against the light excitation is this very fundamental azobenzene systems. Here you see once if we irradiate the azobenzene by the ultraviolet light, the reaction proceeds from left-hand side to the right-hand side, and eventually this molecular molecule will transform into the bent mode. But again, if we irradiate the bent form of the organic substances against to the visible light, again the structure of the molecules will be recovered to the straightforward form in the left-hand side. And this type of the nanoscopic molecular morphological changes can be reflected for the one-dimensional nanowires or not. This is the second question. So we have designed this type of the organic polymer materials composed of the photoresponsive unit embedded into their backbones. And based on these polymer materials, we have tried to fabricate one-dimensional nanomaterials. And as shown in this view graph, at first, as shown in the last slide, one unit are a photoresponsive unit, but the other one, this is a well-known fluorescence. But anyway, here you see the fluorescence is a very photofunctional organic unit, and they exhibit very high fluorescence. And so, as shown in this view graph, the fabricated nanowires also exhibit the high emissions as represented in the bottom lines of the fluorescence microscope images. And fluorescence microscope has a very low resolutions compared to the atomic force microscope spectroscopy. But anyway, once the nanowires can emit the light, we can check about the location of the nanowires simply by the optical microscope systems. And the question is, the morphological changes of the one-dimensional nanowires against the light excitations, and a precise trace of the morphology of the one-dimensional nanowires also checked by the atomic force microscope. And as we expected, actually the morphology of the nanowires was changed from the straightforward stretched form to the wavy zigzag forms in the shown in the bottom AFM microscope images. Here you see we had also succeeded to realize the photoresponsive one-dimensional nanowires by using ion beams. And the further checking of the global morphology of the structure of nanowires was also confirmed by the successive light extensions. And I'm showing this view graph, the ones after the preparation of the straightforward one-dimensional nanowires against the ultraviolet light extensions, the one-dimensional nanowires were changed into the wavy home, as shown in the middle slide, middle panels. And again, the cover to the stretched home, as shown in the right-hand side. In the next examples is the utilization of the huge surface areas of the one-dimensional nanowires. Maybe one of the most representative one-dimensional materials is carbon nanotubes. And the carbon nanotube also have a very high surface areas. But anyway, in our cases, based on any organic substances, we can realize the one-dimensional nanowires with extremely large surface areas. And as I demonstrated in the first part of my presentations, it is very easy to combine the several kinds of the organic substances into the one single straightforward nanowire system. So such kind of the protocols to realize the multi-functional nanowire materials can be applicable to the sensing platform reflecting their extremely large surface areas. So we have designed this type of the nanowires where which is composed of the one unit where the energy harvesting of the for the photoirradiations, and energy was transferred to the some specific point of the nanowires and exhibit the photofunctionals at the part and shown in this slide. And I'll show in this micrograph. I'll show in this micrograph of the fluorescence microscope images. Actually, once if we irradiated the samples to the one segment where only the ultraviolet light extensions, ultraviolet light absorptions, the energy harvested energy at the one part of the nanowires was transformed to the another part of the nanowires and exhibit the red light emissions where the functional unit was embedded. So in this, as displayed in this view graph, the energy was transformed one segment to the other segment. And so such kind of the sensing materials also realized by the single particle nanofabrication techniques developed by ourselves. And next question is, we would like to extend the feasibility of these techniques for more wider organic molecules, not only for the polymeric materials, but also the other extremely large variation of the organic small molecular systems. And as you know, that in case of the polymeric materials, any polymeric materials was polymerized based on the small monomer materials. And so if you can realize simultaneously the polymerization reaction and the cross-linking reactions against the small organic materials, this type of the single ion induced nanofabrication techniques can be applicable for the nanomaterial fabrication based on any kind of organic materials. So next our challenge is to find out the efficient polymerization reaction systems caused by the high energy charged particles. And as you may know, that's the protocols to fabricate the polymer materials. The polymerization reaction was categorized into the several systems. Of course, in case of the very precise polymerization reaction was mediated by the very unstable chemical reactive intermediates. However, in the industrial processes, most of all the polymeric materials can be polymerized via the neutral radical reactions. And so at first, we are focusing onto the neutral radical formations, reactions, polymerization, and finally cross-linking reactions. Though our target is to realize most of all the initiation reaction of the polymerization, propagation of the polymerization reaction, and cross-linking reactions as highly effective as possible. And so we start to find out the ideal unit to promote this type of the chemical reactions. One of the examples of organic substances where we can promote the highly effective polymerization reaction is Buckminster Fluorescent systems. And here I summarize 4 examples of the Buckminster Fluorescent systems. But anyway, starting from the very fundamental C60 molecules to the functionalized the Buckminster Fluorescent system. Most of all the Buckminster Fluorescent molecular systems can cause the highly effective initiation reaction and polymerization reactions, as well as the cross-linking reactions. And eventually, we could obtain the very clear formation of one-dimensional nanomaterials based on this type of the small molecular systems. And surprisingly, with the functionality embedding into the small organic materials, the chemical reaction was enhanced, and eventually we got the thicker nanowires as shown in the right panel of this slide. And one of the our surprising about this result is, the nanowires has a signature of the C60 represented in the nanowires. And as shown in the very high resolution atomic scanning tunneling microscope images, we can see clearly the signature of the C60 molecules themselves. And just like the sweet cones, the C60 molecules kept their morphology even after the radiation-induced polymerization reaction by the high-energy charged particles within the ion tracks. And so this result remind us that we can utilize the photo and electronic functional property of the C60 molecules even after the fabrication of one-dimensional nanomaterials. And as you may know, that the Buckminster Fluorescent system is one of the most key player to fabricate the organic solar cell devices, because the Fluorescent aggregate, Buckminster Fluorescent aggregate, C60 aggregate, can transport electrons very effectively. And so if you can facilitate the interfacial structures between electron donor to the electron acceptor, here in this case, the C60 nanowires should be acting as the electron accepting unit. But anyway, after the photo-induced ionization reactions, the electron can be transported along the one-dimensional C60 nanowires, and eventually we might fabricate the solar cells. This was our ideas, and the result is very clear. As shown in this view graph, after the fabrication of the one-dimensional nanowires based on the Buckminster Fluorescent systems, if we overcoated the systems by whole transporting organic materials, the system are actually acting as a highly efficient organic solar cells, and they could give electricities against the light extensions. The next question is, other than the Buckminster Fluorescent system, what kind of organic molecules can give one-dimensional nanowires by a single particle induced polymerization reaction and cross-linking reactions? Next, we moved on to another target of the small molecular system. Here, this is the examples. These are the examples of the nanowires fabricated based on the small amine molecules. And as seen in this atomic force microscope images, unfortunately, in case of the smallest analogs of the amine molecules, that is a triphenylamine molecules, the left top panels, the result was indicated. But in this case, unfortunately, we could not successfully obtain the one-dimensional nanowires. But surprisingly, all the 5 small molecular candidates gave a very clear one-dimensional nanowires. And so this result also suggests us that, extremely wide feasibility of the single particle nanofabrication techniques for a variety of organic molecular systems. And what happened inside of the ion tracks? This is the next question. So we next try to identify what kind of the chemical reactive intermediates was generated and formed, and what kind of the propagation reaction to make polymers were polymerization occurs, and eventually why such kind of chemical reaction was confined within the very small cylindrical areas along the single particle tracks. And so after the isolation of the nanowires, again and again, we have washed the nanowires by some kind of solvent, which it can dissolve the organic molecules before the irradiations. And so soon after the isolation of the nanowires was clearly kept the morphology with one-dimensional manners. However, after the washing again and again, nanowires was gradually dissolved and fragmented eventually, as shown in the right-hand side panels. So in this case, the cross-linking reaction of the generated polymer material is not completed. And so still the small amount, some fraction of the organic molecules can be dissolved against the organic solvent. So we can control successively the morphology of the one-dimensional nanowires. This result clearly suggests. And what was the reactive intermediates to promote the polymerization reactions? And as we expected that, soon after the ion beam radiations, the nanowires clearly suggest the presence of organic radicals. And this result suggests that the chemical reaction was mainly predominantly promoted by the neutral organic radical mediated chemical reactions. And also, as demonstrated in the previous slide, that some portion of the nanowires could be dissolved by the organic solvent. And so, as seen in the view graphs in the upper panels, the molecular weight of the organic molecules enclosed in the nanowires is not so large in this case. And other than we also try to enhance the chemical reactivity of the organic materials by introducing some kind of functional groups into the organic molecules. In this case, we have introduced in the vinyl groups. This is a very well-known polymerization unit to obtain the commercially available polymer materials. And simultaneously, we have tried to introduce the halogenated atoms into the molecules. And as shown in these three micrographs, other than the unexpectedly, other than the binary groups, the halogenation of the organic molecules was more effective to promote the highly efficient chemical reaction caused by the ion beams here. And this is interpolated because that, based on the very fundamentals of the radiation chemistry, Once if we introduce the halogenated atoms into the organic materials, particularly for the aromatic molecules, after the ionization of the organic molecules, the electrons should be transformed onto the neutral molecules, and eventually, as shown in this reaction route, finally, the halogenated anions will be removed from the organic molecules, giving neutral radicals of the organic substances. This is the case, giving highly efficient chemical reactions in the single particle polymerization, induced polymerization reactions. And this is a summary about the chemical reactions demonstrated in our systems. And so this clearly suggests that the chemical modification of organic molecules play a key role to promote the highly efficient reactions to give one-dimensional nanostructures. The next step is also to extend the feasibility of the nanowire and organic our techniques to the other molecular systems. And we are using this type of the chiral fluorescence system as a target material. And very fortunately, most of all this type of molecules gave a very clear nanowire. And we also simultaneously expect the photofunctionals of the nanowires after the preparation of the one-dimensional nanostructures. And as expected, this type of molecules exhibit highly efficient light emissions, and seen in this view graph, resulting nanowires was very highly emissive. And the sizes of the nanowires also discussed in terms of the chemical reaction efficiency. And as we expected that here, as in this case, highly efficient polymerization reaction, as well as the crosslinking reactions was promoted by the ion particle irradiation. And as in the previous cases, again, the halogenation reaction also also cause the more efficient chemical reaction, giving thicker nanowires. So this type of the chemical modification also applicable to control the sizes of the one-dimensional nanowires by our technique. Okay, and this is a summary about chemical reaction efficiency. And as in the table, the G value, this is one of the most important parameters to quantify the chemical reaction efficiency. But efficiency was in the ranges of 8 to 10. And this value suggests that actually the chain reaction promoted by the single particle intramolecular reactions. Okay. We go to the another topic here, and so the photofunctional materials are also applicable for the sensing of some other chemicals. And this is a case of the nanowires fabricated for the higher emissive molecular systems, where in the seen in the chemical structure of the molecules, in the right-hand side and left-hand side, the both same molecular subunit was embedded into the one single molecule. This molecular subunit is often called as the ESIPT active molecular systems. And even in the solid state, this type of molecules exhibit extremely high quantum efficiency of the fluorescence, reaching up to the 0.8 or 0.9. And in this case, we could realize the highly emissive one-dimensional nanowire. And very interestingly, this high emissivity of the nanowires, as well as the molecular substances, can be controlled by the interaction with some special chemical substances. That is, as displayed in this view graph, nitrobenzene or the other kind of the halogenated or the cyanobenzene groups. And maybe as you may imagine that, most of all the chemical subunits are often employed as explosives. So whether we can, our nanowires can be applicable for the sensing of the explosive or not. This is the questions. And we have tried to check about the emissivity of the nanowire. And after the exposure to the nitrobenzenes, seen in the red lines, the emission from the nanowires was completely quenched. So reflecting the extremely high surface area, wide surface area of the nanowires, this kind of the nanowire system should be expected to be acting as a highly sensitive sensing platform in the future. And this is a very recent result about the nanowire fabrication based on the photofunctional groups. And in this case, we employed the porphyrin subunit. And based on this porphyrin subunit, we also successfully produced one-dimensional nanowires. And reason why we choose the porphyrin subunit as the target materials is, this type of the molecular core also absorbs strongly the photons, and afterward, the excited energy on the porphyrin subunit can be very easily converted into the chemical energies. And so this is a case of the more efficient light harvesting that, in this case, the porphyrin nanowire was coupled with the metal nanoparticles. And as you know, the metal nanoparticles has a very strong plasma resonances. So the plasma resonance energy was directly converted into the porphyrin nanowires and successively converted into the chemical energies, as demonstrated in the next view graph. In this case, after the excitation of the plasma metal particles and converted into the porphyrin nanowires, the excited energy was again converted into the chemical energy. In this case, this is the excitation to the oxygens. And so, as you know, the ground state of the oxygen molecules are triplet state. But anyway, after the energy conversion from the porphyrin nanowires to the oxygen molecules, triplet excited oxygen molecules was generated. And so as this demonstrated in this view graph, the nanowires, upon the excitation to the ultraviolet light or the visible light, the highly efficient excited oxygen molecules was generated. And so this result suggests that nanowire are also applicable for the future medical treatment to cure the unusable, unpreferable, the cancer cells or the other kind of the biomedical reaction in our human bodies. And as you may know, that in our case, the sizes of the nanowires was completely under control. The length of the nanowires was completely uniform because the nanowires was generated from the top surface to the bottom surfaces of the thin films of the target. So we can control the size precisely at any ranges. And so such kind of the size controlled nanowires also can be very effectively captured by the living cells. So this is the reason why we are claiming that our nanowire system is also applicable for the future as a medical treatment systems. And again, back to the Buckminster Fluorescence systems. As you may know, that as you see that in the previous slide, the Buckminster Fluorescence gave a very straightforward nanowires. And almost all in the case, we often employ the protocol to remove the unreacted part of organic materials by the solvent treatment. So, initially the molecules can be dissolved into the organic solvent, and after the irradiations, unreacted part of the organic substances was removed by the dissolution process by the organic solvent. However, to remove the unreacted part, we don't have to use the organic substances. For instance, in this case, Buckminster Fullerene has a very low, but the certain boiling vapor pressures. And so by the sublimation process of the unreacted part of the molecules, we can remove very efficiently completely in the dry process to isolate the one-dimensional organic nanowires. And as seen in this view graph, that completely straightforward, the standing nanowires was realized by the sublimation removals of unreacted part of the nanowires. And such kind of the very clear standing nanowires also extend their feasibility for more wider application areas. And for instance, the more highly efficient sensing platform or medical application or the energy converting systems. This is a summary of my talk, but anyway, starting from the very fundamentals of the ionizing radiations, we can realize the material fabrications by using single isolated particles. And for the future, we are now imagining this type of the prospect that, we will design the multifunctional nanomaterials on demand to any field of the applications. And so combining the functionals of the organic materials, we will design the not one-dimensional nanomaterials which perfectly fit for the future applicational areas. So thank you for your kind attentions. Thank you very much.
Thank you, Professor Seki. Let us now see if the participants have some questions to ask. Participants? May I ask you a question, sir?
Okay, yes, please.
Actually, you had observed that polymerization throughout the track size may not be complete sometimes, and while etching, these wires can break. So is there any post-irradiation process by which we can complete the polymerization?
Mm-hmm.
So can you suggest?
You're right, and as in some cases the polymerization was completely completely finished. And as you know, that in our cases mostly we are using the neutral radical mediated chemical reaction. So you are correct that after the ion beam irradiation and during the processing or after the irradiations, again, if we generated neutral radicals into the nanowire systems, finally the chemical reaction should be completed. And one of the protocol to promote the radical induced reaction is using the oxygens. And so after the successive treatment, by the successive treatment after the irradiations, we might complete the polymerization reaction as well as the cross-linking reactions. So this is very good ideas. I will try it.
Okay, thank you, sir.
Hi, Professor Seki.
Yep.
Yeah, I'm Furnishing from IUAC.
Sure.
Can you make some comment about the microstructure of such nanowires, the kind of defect structure, and and they do give it?
This is very important question, as you know, that once if we taking the very fundamental models of the ion tracks, as you know, the ion track cores and penumbra, or in terms of the halos, most of all the nanowires, the sizes of nanowires was distributed in the range of the halo or the penumbra areas. So what happened at the inside of the nanowires, particularly at the areas of the cores? As you suggested, that the deposited energy densities in the core area was extremely high, and we speculate that the chemical structure at inside of the nanowires no longer maintained, and molecules themselves are completely damaged by at the core areas, and this also mimics remind us that the core after the successive treatment after the isolation of the nanowires, particularly emerging chemical treatment, we can dissolve again only the core part, eventually lead the tube structures. And now we are trying to realize such kind of the one-dimensional materials. So thank you very much for your the comment.
Oh, thank you very much. Thank you.
Professor Seki, one of the participants has asked you something. Can I read from there?
Oh,
yes. He's asking, how do we measure the sensitivity property, and whether it is possible in UV-Vis spectroscopy?
Sure. Yes, I can see the comment. One of the highest measure for the sensitivity of the chemical reaction or sensing is the chemical ones, not the optical ones. For instance, the sensitivity, once if you can trace the sensitivity by the chemical reactions, we can check about the sensitivity as low as maybe 10 to the third or 10 to the fourth lower ranges compared to the optical ones. However, once the optical spectroscopy, we can confirm the sensitivity of the systems, it is applicable for the wide range of applications. So this is the reason why we choose mainly the optical protocols to check about the sensitivities. And so if in the case of we are interested in the more lower sensitivities, the alternative to check about the sensitivity is the chemical ones, I think. And in case of the spectroscopy, the highest sensitivity or highest protocol to check about sensitivity is the spins, I think. And so even in the field of the chemical reactions, electron paramagnetic resonance, or the EPR spectroscopy, or electron spin resonance spectroscopy, might have highest sensitivities. And also the other ideas to realize higher sensitivity is the use of the resonance. So this is the reason why we use the plasmon resonance in the last part of my presentations. And so in that case, we can expect the 10 to the 10th times higher sensitivity checking. And so maybe, I guess, not only the spectroscopy technique, but also by utilizing the other kind of protocols, we can realize the extremely wide dynamic range for the sensitivity checking with the regime of the 10 to the 10th, I think.
Can I add little comment to it?
Oh, yes. Can we prepare the graph?
Maybe we can say that it cannot give the quantitative information about the sensitivity, but some qualitative indications are there that whether system is more sensitive or less sensitive. So, therefore, it is very difficult to make some quantitative estimation about the sensitivity using the UV-Vis spectroscopy technique.
Oh, sure. Yes, I agree with you.
Yeah. Thank you.
And the next question is, can we prepare the graphene oxide carbon nanotube by spent method? Well, this is a very good question. So here's for the polymerization reaction mediated nanomaterial fabrications. At first, we focused onto the Buckminster Fluorescent systems. And this is a reason why that, we would like to realize the carbon-based nanomaterials, because the Buckminster Fluorescent is principally the carbon allotroph. And so after the successive formation of the carbon-based one-dimensional nanostructures, in principle, it is possible to fabricate a graphene oxide system, because the oxidation reaction of the carbon-based nanowires are very easy by using a variety of chemical treatment. So in principle, I should say that it is yes, that we can prepare the graphene oxide in the future.
Participants, any other question? I guess there are no more questions.
Okay.
So participant, we just now listen to the talk, very good talk, very interesting talk about the application of ion beams to fabricate nanostructures. So let us now thank Professor Seki for delivering this very interesting and informative talk.
Thank you very much. And I'm looking forward to meet you again at the IUAC by using the Accelerator setup. Thank you very much.
Sam, I would also like to thank Professor Seki for a very excellent lecture. It was very nice and is refreshing to hear him.
Thank you very much, Professor Tripathi. I also would like to meet you again. Thank you.
Yes,
thank you. Yes. So now we can move to the second lecture. And in the previous lecture, we saw that ion beams can produce damages inside material. And one of the technique to evaluate means loss in crystallinity is by ion channeling and in channeling. So the next talk is on that by Dr. Sundaravel. So before his talk, I would like to give a brief introduction about the next speaker. So he is Dr. Balakrishnan Sundaravel, who is Scientist G in Material Science Group of IGCAR, Kalpakkam. He did his MSc from Madurai Kamaraj University in 1988. He received PhD from Utkal University in 1999. And he was postdoctoral fellow from 1998 to 2001. Thereafter, he joined IGCAR in 2001. His research interest lies in ion-solid interaction, ion beam analysis, defects, strain, orientation in epi layers, thin films, spintronic materials, irradiation effects on advanced materials, impurity defect interaction in metal crystals. And he has published more than 135 papers in journals. So he will be described today about ion channeling in material analysis in his lecture. So now let us hear from Dr. Sundaravel. So sir, you may please start your presentation.
Thank you, Professor Saikhan, for your nice introduction. Can you hear me?
Yes, sir.
I thank Professor Ashokan and the organizers of IBMS school for giving me opportunity for giving a lecture in this prestigious school. And let me share this PPT file. Can you see the screen, please?
Not yet, sir.
Just wait me, please.
Sir, you can press the present now option.
Okay.
Present now arrow, one arrow must be there. You just click on that lower ribbon where you can mute and unmute your audio. There is an option of present now. One arrow is there.
Just let me try.
राइट साइड में लोअर पार्ट देखिए.
Right side lower part.
So did you find the option present now?
No, not yet. Yes, present now. Yes.
Present now. Click on present now. Then it will ask you what to share. So
Yes.
you select a window. It must be giving you option of sharing entire screen or a window. So you just select a window option from there. Yes, sir, it is coming. It's coming. So your presentation must be minimized. So you just click on that. Click on your PPT, sir. Minimize ribbon, yeah. Yeah, now you go to slideshow. Slideshow. Yes, sir. Now it has come.
Can you see?
Now.
Yes. Thank you. I'll be talking on ion channeling for materials analysis, and I am from IGCAR Kalpakkam. Kalpakkam is close to Mahapalipuram, which is 70 kilometers south of Chennai, where you can see the 5th century monuments, Sor temple across the Sor, and also you can see this Arjuna's Tapas and Pancharathas, which are famous tourist attractions nearby. And I'll be discussing about the concepts of ion channeling, and I'll tell how we align the crystals with the incident beam direction and some of the applications of channeling. And as such, for detailed understanding, one can go through two books, one by Professor Chu, Mayer, and Nicolette, and also another book by Feldman, Mayer, and Pickrax. In IGCAR, we have 4 accelerators, and most of our experiments, ion beam analysis and ion implantation, we use this 1.7 MV Tendertron accelerator. And in our accelerator, there are 3 beam lines, and most of our studies we do it in this plus 10-degree beam line, where we can do ion implantation and ion beam analysis techniques like Rutherford basket ring, elastic recoil detection, X-ray, nuclear reaction analysis, and EDA. And here in plus 30-degree beam line, have a high resolution RBS, where we can have energy resolution of something like 2 keV. It's 1.6 keV we can have, and depth resolution is 2 to 3 angstroms. And then there is minus 10-degree beam line. It is a UHV beam line, and here we can do high temperature implantation under UHV conditions. And this chamber, it is also coupled to a 400 kV accelerator with another UHV beam line. As such, here you can see this schematic here, where on the sample, 2 different ions, one from 1.7 MV Tendertron accelerator and another from 400 kV accelerator, both meet this beam, and we will be able to do dual ion irradiation with this UHB beamline. And this is a 400 kV accelerator which is here, and there is one 1.7 MV. This one is 150 kV accelerator where we have a RF ion source, and we can do ion implantation in this one. And recently we have installed a state-of-art 200 kV accelerator in UGCD CSR, which is just close to our campus. And we have a beamline in VCC Calcutta, where we can irradiate with 30 MeV protons, and we are setting up a beamline there for doing inside to creep measurements. And now coming to channeling, as such, this ion channeling is an extension of Rutherford backscattering spectrometry, and everyone know about this Rutherford backscattering by now, as Professor Oja and Umapati, they have discussed in detail about this Rutherford backscattering technique. And experimental setup is almost the same like Rutherford backscattering, where on the sample a collimated parallel beam is incidenting, and we look at the backscattering ions with a surface barrier detector. And only difference is that our sample is mounted on a goniometer, where the crystal can be tilted about this beam axis, and as well as it can be rotated about this beam axis. And we find the alignment condition. Once the beam is exactly aligned, then there will be a drastic reduction in the backscattering. Here, for example, this is in the left side, whatever is shown, it is a silicon crystal, and we shoot with incident beam, look at the backscattered ions, and the spectrum, whatever is shown in the data, this dashed line, this corresponds to Rutherford backscattering along random orientation, normal RBS. Okay, once this beam is aligned with respect to the crystallographic atomic strings, then what happens? This incident ions get steered into the crystal, and only the top atomic layer is visible. Since top atomic layer is visible, corresponding to that monolayer, you get a surface peak here, and underneath there is not much backscattering, and we see much reduced yield. And we can find what is the crystallinity of the crystal from the ratio of this backscattered yield in channeling spectra to the random spectra. That is called chi minimum. It is a measure of crystalline quality, Ya by Yr. Okay, so for very good crystals, this chi minimum value will be something within 3%. That means that suppose if 100 particles are getting scattered in random direction, in aligned direction, only less than 3 number of particles will be getting scattered. Suppose if there are two different elements in the top layer grown on the substrate, then in RBS you know that ion scattering from heavier atoms will be coming at higher energy, and ions getting scattered from lighter atom will be coming at lower energy. Much lighter atom that will be coming at much lower energy. And once we align the beam, then there is drastic reduction in scattering signal from all the elements, from top layer as well as this bottom substrate layer. And suppose you have some very thin silicon dioxide or some other thin material in on your sample. Under the aligned condition, say for example this bottom one, whatever it is a random direction. Say compared to random direction, if you see the backscattering in the aligned direction, this whatever background is coming from substrate, that will be much less, and one can have enhanced sensitivity for light elements using this technique. And as such, there are many applications of this ion channeling, and I will discuss some of this channeling, some of these applications, like determining crystalline quality, then determining how much is the mosaic spread, lattice site location of an atom. You see, for example, in silicon we can dope with either p-type or n-type dopants like boron or phosphorus, and n-type or p-type silicon, only when the dopant impurity atom, it stays exactly in the substitutional atom position. That is, you are taking out a silicon lattice, silicon from the lattice position and replacing in that location this dopant. Then only your dopant property will be there. So you can find whether that your dopant impurity is exactly sitting in substitutional or interstitial position. And suppose you are having a epitaxial layer grown on substrate, there will be strain due to lattice mismatch. So you can determine strain in this material, and also you'll be able to find this. Sometimes it happens that the epilayer orientation, it can get slightly tilted with reference to the substrate orientation. So we can find that tilt angle, and also in plane orientation, say to match with the lattice of the substrate, this epilayer orientation, it can get rotated with respect to the substrate. So one can see whether there is any in plane orientation of epilayers, and one can determine the type of defects, whether it is point defect, dislocation, or stacking fault, and what is the density of those lattice defects, that one can determine. And suppose you have point defects in the material, then what is the defect concentration as a function of depth, that we can see. But point defects here, I mean only the interstitial defects, vacancy defects. Only interstitial defects it is sensitive. And for vacancy means one has to go for positive annihilation techniques, and one can determine whether mixed phases is there or not. For example, if you take gallium nitride, there can be cubic and hexagonal phases, and it is possible to do with XRD. And similar to that, with using channeling also, we can determine this presence of mixed phases. And polarity, for example, if you take gallium nitride, whether the top layer is terminated gallium or top layer is terminated with nitrogen atoms, we can tell what is the polarity of that substrate. And if you do the experiments under ultra high vacuum, as such, the surface lattice, it will be getting reconstructed. It won't be of the same lattice like the bulk, and we'll be able to study the surface reconstruction with this technique. And also we can determine this structural phase transitions. And as such, if we see this, we are studying crystalline materials with ion channeling, and normally people use X-ray diffraction, electron diffraction, all these techniques for using this for studying the crystals. And for channeling, we are using MEV helium ions, and the wavelength of MEV helium ions, if you see, it will be something like 10⁻⁻12 centimeter. And as such, whatever helium ions at this energy you are putting, the lattice, it won't be seeing it as a diffraction grating. It will see a crystal of rows and seeds. Here, as such, if you look at say diamond crystalline material, when the crystalline material is in random orientation, you can see a lot of atoms, and if you can tilt the crystal and at certain angles, you'll be able to see a set of planes. Okay, and if you incident the beam along these planes, then it will be like nuclear charges. Yes, seeds of nuclear charges are there. In between the seeds of nuclear planar charges, the beam will be getting steered in. And if you align the crystal still better and along the specific axial direction, if you see, you'll be seeing a lot of channels. Okay, and if you see each atom at the top, below it there is a atomic string, something like this, and incident beam, it will be getting steered into this aligned channels when we align this beam, and as such, this since this atoms are aligned something like a string, we can approximate to continuum potential, and the continuum potential is given by this expression UAFR equal to UAFR is equal to this expression. So it assumes some nuclear charge per unit length, and this sort of in this potential it is working, and as such, when we are aligning this beam with respect to different axes, basically you get minimum yield, and about that one, if we tilt it little bit, then from the minimal axis it will go towards the random position. And how good is that minimum for different for example, for different planar direction? Okay, for example, for diamond crystal, if you see this 110 plane, that will have the lowest chi minimum value, and next it will be followed by this triple one will be slightly higher chi minimum. That means the reduction will be less in this one, and here it won't be that much reduction. Okay, this one you have a lowest chi minimum value, better channeling. And for corresponding diamond, if you look at this axis, it follows similar like the plane. But if you take FCC or BCC, for example, for triple one plane is the deepest, but in FCC case, 110 plane is the deepest. 110 axis is the deepest. And when you shoot the beam along this axial direction, I told that only the top layer atoms are visible. These underlying atoms, as such, they are shadowed by this shadow cone, and that's why we get the surface peak, which is coming from the top layer atoms, which is just one atomic layer. And as such, this radius of this shadow cone is given with this expression, and it is inversely proportional to e power half. So when energy is low, your shadow cone radius will be large, and when shadow cone radius is large, then as such, for larger angles with respect to the incident axis also, you'll be able to get channeling. But once you go for higher energy, the shadow cone radius is much smaller, and even for small tilt, it will get dechanneled. And as such, when the incident beam is aligned with respect to this beam, only there is a small angle collisions between the string and these atoms, and how close this incident ion can go close to this incident string. it is of the order of this RMS thermal vibration amplitude. RMS thermal vibration amplitude is of the order of 0.1 angstrom. So sensitivity of this technique is something like 0.1 angstrom. So when the ion goes something close to 0.1 angstroms, then it can get backscattered by this target atom. And as such, this potential, whatever people take for describing this channeling is screened Coulomb potential in Molary approximation of Thomas Fermi's potential. And as such, if you see this energy of these incident ions, as such, when it is at the center of the channel, it has highest kinetic energy, and this energy we can split it into three components along x, y, and z. Z is that incident direction, and xy is this perpendicular direction. Okay, and this UR4 is this potential, and out of this, as such, in channeling this along the z component, that energy is unaffected, and when the beam is passing through this crystal, only this energy, as such, this transverse energy, that will be conserved. For how it is conserved, as such, when it is just in the middle of the channel, at that time this kinetic energy is more, and when the beam goes closer to the string, as such, kinetic energy will be going on decreasing and potential energy will be increasing, and then it will be going some small angle collision, and it will be getting deflected. And what is the maximum angle we can tilt so that that small angle collision will take place? That angle is defined as critical angle of channeling, and this has much information about your string potential and all. And this angle psi c, this is critical angle of channeling, and that's given by u r minimum. This r minimum is something close to the r minimum is the distance between string and this incident ion at the time of that collision. So what is that potential at r minimum divided by the energy? Okay, and this psi c we can experimentally measure, and as such, it is given by this expression. And as such, when you align the beam exactly on the crystalline direction, I told that there will be minimum backscattering or minimum value of chi minimum. And then when you tilt the sample out of the axis, this yield will be going on increasing. And when you go something like 2 degree off or so, you'll be getting a higher value. It is close to the normal RVS yield value. Okay, and whatever is this width, this is 2 times the psi f, and the psi f is connected with that critical angle of channeling. And that psi f value, as such, one can approximate with this continuum Molary potential, and psi f value is given by this expression, and that ratio of this yield along as such, this value, say ratio between minima and this random value, that is chi minimum, and that is proportional to number density of atoms. D is distance between the two atoms along the string. U1 is thermal vibration amplitude, and A is Thomas Fermi screening radius. As such, once you know this atomic density and thermal vibration amplitude for that specific crystal, then theoretically you can calculate this chi minimum value, and if experimental value is close to this, then we can tell crystal quality is good. And if you look at what sort of stopping mechanisms are there, in normal Rutherford gas scattering, as such, there is random collections, and in energy loss, there will be both nuclear as well as electronic contributions. And in channeling, it is only some small angle collection. That nuclear energy loss is negligible. Only it is dominated by this electronic energy loss. And this is our typical ion channeling systems. We have a 6-axis sample goniometer where we can mount the sample inside this vacuum chamber, and sample can be tilted about this beam axis, and also it can be rotated. And this goniometer stepper motors are automated, and as such, for aligning different type of methods are there. We follow the method given by Professor Chu in his backscattering spectrometry book. And in this one, what we do is we mount the sample on the goniometer, and from the normal direction of the sample, we tilt. This is the normal direction, and from normal direction, we tilt the sample by 5 degrees. And by tilting at 5 degrees, for a fixed charge, we collect what is the backscattering counts. For example, this is the Rutherford backscattering spectra for gallium arsenide, and in the right side bottom, we are seeing this Rutherford backscattering. This green color one, it corresponds to the random spectra for gallium arsenide. In this one, we take a small energy window in this high energy side, okay, and in that one, how much is the total counts? That counts for a fixed charge we find for a specific angle. Angle theta is kept at 5 degrees, and by keeping the angle at 5 degrees, from gallium arsenide, as such, we cannot resolve this gallium and arsenic masses, so it looks like a single error function set of thing. And by tilting it, when we rotate, whenever you come across some plane, you see reduced yield, and we get many dips, something like this red color curve. And this gallium arsenide is a zinc blende structure. In this one, it has a much lower time minimum. So 110 is a deeper, and cellular one is a 100. So say once you scan with respect to the axis, like in this left hand schematic, you'll be getting different peaks. Our tilt angle is 5 degree. We are turning the sample from 0 to 360 degree, and we find what is the yield of this gallium plus arsenic signal in this high energy side. Okay, we take high energy side because there only more reduction is there, and we get this sort of dips from 0 to 360 degree. And then these dip positions, for example, here pi value is something close to 15 degrees or so. So we take a polar plot. In polar plot, at the center, whatever is the point, that is the normal axis. Okay, there and pi is also 0. Then sample by 1 degree. Okay, you tilt the sample by 1 degree, and at 1 degree tilt angle, we just make that axis precise about this center. Then you get a cone, and the projection of the cone is a circle. Okay, so this the value of this circular position, that tells about the angle theta value. Okay, this, for example, this inner circle, this whatever is the first circle, that corresponds to theta equal to 1 degree, and pi varies from 0, here 90, 180, 270, 360. So this corresponds to 1 degree theta. Next one is 2 degree, 3, 4, here 5 degree. Since we kept the angle at 5 degree, this dip positions we mark. Okay, So 8 prominent dips are there. So we mark these 8 prominent dips, and then if you want more precise alignment, one can do, instead of 5 degree, one can tilt by 6 degree and take one more spectra like this. Then those points also can be plotted, and then we join those points. Okay, we join those points in upper quadrant with respect to the lower quadrant, and then we all the lines in this polar plot, they'll be meeting at one point. Okay, at that point, find out what is the value of theta and what is the value of phi, and we set that value of theta and pi, and at that position the crystal will be aligned, and under aligned condition, if we take normal Rutherford basketing, you see that here whatever you see, this blue color curve, where there is much reduction. Here our time minimum value is something like 3%, and in case in the crystal, if you do some implantation, due to the presence of defects, there will be dechanneling, and as such, from this dechanneled spectra, we'll be able to get that defect density as a function of depth. That I'll be coming to it later. And about this axis, if you tilt plus minus 2 degrees, then you'll get this sort of curve, and this width of the curve gives the psi of values. And if we connect a cryostat to the sample holder using a copper braid, sample temperature can be lowered, and we'll be able to do the channeling at lower temperatures also. And when we align this beam with respect to the crystallographic direction, at the center of these atomic channels, we'll be having higher incident ion flux, while towards the outer edge of these channels, there will be lesser flux. And if you find this tilt angular scan about these directions, we look at signal from substrate as well as the dopant atoms. In case if the dopant atom is substitutional, then as such dopant atom we are marking with this dotted lines. So the host lattice as well as the signal from that impurity, they'll be following the same curve. Okay, tilt angular curve. This is substitutional. Suppose if you have some impurity atom at the middle of the channel, then that impurity atom, it will be seeing the high dense flux. Okay, because of that, if it is interstitial, then at the bottom left of this curve, whatever you see, you'll be seeing some sharp bump. Okay, and if this curve is like this, then we can tell that impurity is in interstitial position. Suppose if the crystal has some other defects, then the impurity atom, say this is the host lattice position, and this dark spot, it is the impurity. If it is moving towards the center of this channel, seven, and from that one we can find what is the lattice position. Okay, even for small shift of 0.1 angstroms, we can see much change in shift positions. And for locating the actual position, we have to do at least channeling at 2 different axes. For example, you are seeing a case where this impurity is in this whatever is cross square position. Okay, in this position, if it is there along 100 direction, it will appear like aligned condition, but in between it will be seen as interstitial. So only when you do using triangulation technique at 2 different axes, you will know what is the positions. Here I am showing one tilt angular scan. Say where we have implanted manganese in gallium nitride, and this this is RB spectra and spectra corresponding to unimplanted sample and this implanted sample of channeling. It is given here, and in this one only this gallium signal is visible, and for gallium intensity we take the signal here. For looking at signals from M1 inside to we see the manganese pixie yield, okay, and that corresponding pixie yield we plot for manganese, and this manganese signal, it is following more or less this gallium signal, but the dip position is slightly tilted, and if it would have been substitutional 100%, then it will be, but some defects are there, so you are seeing the dip is not matching exactly here, and one can find how much is the substitutional fraction. Okay, we see that there is 66% substitutional fraction in this one, and some 0.1 degree tilt of this M1 dip position. That means that there is some gallium manganese nitride nanocrystal. Crystal is not single crystal, but it is having some with reference to substrate. There can be some small tilt orientations. Okay, so in that case, what will happen is for ideal crystal, it would have been like this dotted curve, but due to this mosaic spread, where you are having some plus minus some small angle of misorientation of this domains, it will be somewhat broadened. And if you take this tilt angular curve for different energies, and you plot this whatever is this width of the square, width of this curve square divided by z1 by e is the energy, then one can find the slope, and that slope will give information about this mosaic spread sigma. And the top layer, it can get tilted. For example, here silicon planes are here. When you are growing silver, silver planes are tilted by something like 0.3 degrees, and this tilt can happen either because of vicinality. Normally crystals are cut at some specific angle, so it can depend upon the angle of vicinality, or if there are some 60-degree dislocations, they also can give some tilt. So from whatever is the tilt, if you are taking signal from top silver layer, it is signal is here, and silicon it is here, and from this one we can tell there is some tilt of 0.4 degree. If you take this gallium nitride on sapphire, there is no tilt. So both gallium signal and aluminum signal as such they follow the same position. And here it is a case of buried cobalt disilicide grown using ion beam synthesis in silicon. So you are having top silicon and bottom is cobalt disilicide. And if you look at this curve as such, this is cobalt signal coming from the buried layer. And if you look at silicon, this high energy edge here, you see silicon coming from top layer. In the dip corresponds to silicon coming from COSI2, then it is the substrate. And bottom one, you see this channeling spectra, where you can find some tiny features. By looking at these tiny features, for example, this A and B, this corresponds to defects at the interface. By analyzing those things, we will be able to find what is the type of defects and all. And I told that we can measure the strain in these crystals. And for example, the top layer is silicon dioxide and bottom one is silicon. And suppose if the top layer is relaxed with respect to the substrate, then for example, this unit cell is cubic, say, then say substrate is having this sort of red color square, and your epilayer is this one. And when you look at some off-normal axis, say normal direction is 100 and off-normal axis say 110 at 45 degree. When you see both the signals from substrate and this epilayer, they'll be showing same orientation, same dip positions for this off-normal axis. Suppose if it is strained with respect to the substrate, if top layer is getting strained, then it will contract in X to match with the substrate, and to conserve the volume, it has to expand. Okay, when it is expanding, then from the substrate you are getting the position here, and from the epilayer there is some lower angle. Okay, so by measuring this angle difference between substrate and the epilayer, you can find how much is the strain, and the strain, whatever we are determining, it is tetragonal strain. Tetragonal strain is difference between parallel strain and this perpendicular strain. So, for example, in silicon and cobalt disilicide, normal direction is 111. We go for 110 direction, which is at 35.26 degree. The 35.26 degree is theta, and delta theta is here we observe 0.3. One curve is for silicon, another thing is for cobalt. Okay, so from this one we can find how much is the tetragonal strain, and if you know this bulk modulus and all, using channeling itself, we'll be able to find other strains, perpendicular as well as parallel. And here it is strain measurement in another system, indium gallium arsenide on gallium arsenide, and this red curve, it corresponds to 110 off normal axis of indium. Then this is from the bottom layer. You see clearly that there is some shift in these peaks. From these peak positions, we can find how much is strain, and these samples were irradiated with 150 MeV silver ions, and with irradiation we see that as such there is ion mixing, and indium concentrations decreasing with increase in influence, and because of that your strain is decreasing. And if you look at any lattice matched systems like indium gallium phosphide on gallium arsenide, then in off normal axis we don't see much shift. And as such, if we take cobalt disilicide, we can determine what is the in-plane orientation of cobalt disilicide on silicon substrate. Normally, if we grow cobalt disilicide by molecular beam epitaxy or some other deposition techniques, this cobalt disilicide orientation will be rotated 180 degrees centigrade, 180 degrees from the substrate orientation. But when we grow on, if it is rotated, it is called a B-type cobalt disilicide. If it is not rotated, it is A-type cobalt disilicide. When we make with ion beam synthesis, we observe that it is A-type cobalt disilicide where there is no rotation. And for seeing it, what we do is the substrate, we stay in 110 plane, and in 110 plane, if you tilt by 35.26 degree from 111, you see 110 direction. That is deepest planar dip, deepest this actual dip. And in the other direction, if you tilt 35.26 degree, you'll be seeing 114. That 114, it is a that one as such, it won't be much deep as 110. It will be shallow. Okay. We look at this signal for both substrate and epilayer. Suppose if these dips follow same thing like the substrate, we can tell that there is no rotation. For example, in our case, if we see this for both epilayer as well as substrate, we see deeper dips along 110 direction and shallower dips for 114 in other side. So it is A-type cobalt disilicide. Suppose if there is no rotation, if there is rotation, so whenever 110 is deeper, at that place you may be getting 114. And earlier I told about this in-plane. Say for locating the axis, we are rotating this sample from 0 to 360 degree. That signal, if we take signal from substrate as well as this epilayer, for example, here epilayer is this red color one. Sorry, epilayer is this blue gallium, okay, and aluminum is substrate. And in that one, in this gallium nitride on this sapphire, we see this 112/0 for substrate and epilayer, both are coinciding. So there is no plane rotation in this sample. And another system, if we take LCMO on strontium titanium oxide, and if we do vacuum annealing, okay, before vacuum annealing, if you see, there is no rotation between this LCMO and strontium titanium oxide. So 110 is coinciding with 110 of this substrate. And upon vacuum annealing, there is loss of oxygen and there is some change of structure, and in-plane rotation turns by 45 degrees. For example, when the dip is 110 for LCMO, for STO, it is 100. So from this, we can tell in-plane rotation is there or not. And as such, when we do implantation along this channeling direction, your damage will be much less compared to implantation along random orientation. And upon irradiation, we can, for example, here whatever you see, it is RBS spectra from silver thin film on silicon, and this is the channeling spectra for as deposited sample. And upon annealing or upon irradiation with 1 mu silicon ions, you see that this damage is getting as the layer is becoming more crystalline, which is seen from the reduced yield. For gallium arsenide, if you do the irradiation, that self-annealing will be faster. Okay, here with TEM, people have shown that earlier upon irradiation craters will be there. If you leave it for some time, those craters will anneal out and it will be decreasing. Same thing can be seen with RBS. Initially, damage will be more, and after some time, if you take, that yield will be reduced. We have done some low temperature experiments in gallium arsenide also. And at the low temperature, if you do the irradiation, there won't be self-annealing and damage will be more. But the same thing if you do at high temperature, at room temperature, as such, there is due to self-annealing, the defects produced is less. And at low temperature, if you do this, if you look at this tilt angular scan, that width will be little larger compared to room temperature, because your RMS thermal vibration will be less there. And then in the case of gallium nitride, I told that we can find mixed phases with channeling. So about this normal axis, if you tilt by 35.26 degree, then one can see a 110 orientation in one side and 114 in another side. And this sample shows that there is this cubic phase from green color shows this cubic phase content, and this blue color tells about your hexagonal content. It can also be seen with XRD. So different peaks corresponds to different components corresponds to different phases, and one can tell about. I don't have much time. I will try to take some another 5-10 minutes. One can tell about this type of defects using ion channeling. And if you look at the ion implanted samples, as such, this one is here, whatever you see, this is unimplanted sample. But in an implanted sample, if you see the channeling spectra, you see slightly higher yield. And in this yield, there are two components. Whatever is seen with the dotted line, that corresponds to dechanneling, while other one is coming from this direct scattering. And as such, when the beam is getting scattered with point defects or dislocations or stacking faults, they get dechanneled. And those dechanneling we study as a function of energy. And the dechannelling probability, if you plot as a function of energy, each type of defect will have different energy dependence. For example, for dislocations, we cannot tell whether it is vacancy type or interstitial type, but as such, we can tell there is a dislocation and there is energy dependence of e power of, and if stacking faults are there, there won't be energy dependence, or when vacancies also no energy dependence. For interstitial defects, there will be e power minus of. When point defects are at random position, then it will be e power minus 1. So by seeing this energy dependence as well as these slopes, we can tell about this type of defects and how it is sensitive to point defects. As such, this point, if you see that point defect, it is simply like normal. If that scattering cross section is like normal Rutherford backscattering cross section. Say here you are having 1 by e power 4, and for point defects, you have to integrate this cross section from angle psi c to pi. If you integrate, it shows 1 by e. So that's how we get this e power minus 1 there for point defects. In the case of dislocations, for example, say your that as such, when beam is seeing some edge dislocation like this channels just bend the beam, and in this bent angle, as such, whatever beam is bent within psi c, those things will be steered into the crystal. And suppose from the core of this channel, the psi c is coming at position x0, then the sigma d is 2 into x0, and as such, this cross section, it is having inverse relation between x0 and critical angle. So we'll be having this as such, psi c is having e power of. Since it is inverse of psi c, you are having e power 0.5 for dislocations. When you look at the stacking faults, as such, it is something like some when beam is falling, beam will see the presence of dislocation as a new surface, and that whatever scattering happens, it is something similar to this chi minimum, and this sigma d is proportional to this chi minimum, and chi minimum value doesn't have any energy dependence. So you don't have energy dependence in this one. And in cobalt disilicate, from direct scattering, we have studied the type of defects. And I told that from this channeling, interface peaks A and B are there, and that one we can extract these peaks. For example, whatever is shown in the insert here, we can extract this peak A and peak B area. From that one, we can find how much is the number density of cobalt, and that number density of cobalt, how much is coming from the interface peak as a function of energy. If you plot, you are getting these curves, and the slope gives m by e, and this m by e value, you can put it in this expression. This m by e is here, and b is Burgers vector, and n is this atomic density, d is the d distance along this axis. From this one, you can find what is the defect density. And as such, I told that we can find this defect concentration is a function of depth. For that, what we do, say this is RB spectra from random spectra, while lower ones are from channeling spectra from virgin and implanted samples. And we find this, if we divide this one random with channel, we get chi, and difference of chi between aligned and random, that is plotted here as a function of depth. We extract this one, and then we are having delta chi at various depths. Okay, and this delta chi is given by this expression. This nd is defect density by this is total atomic density, and this one is dechanneling cross section, and this is that number density of defects, and dz is something like 20 angstroms. So what we do, we split this layer into many strips of 20 angstroms width, and if you see the top layer 20 angstrom, there as such we know this delta chi for the top layer. This some value is there, and this n is atomic density, and there is no dechanneling. This part is 0. So for top layer, number of density of defects will be nd equal to n into delta chi. That is for the top layer. Then when you go for the second layer, you'll be having delta chi from this curve, and then this nd is at defect at the second layer, defect density at second layer, plus whatever value you calculate for the top layer, that one you put it, multiply with this 20 angstroms. Then from that one, you can find what is the defect density in second layer. If you look at the third layer, here it comes to the defects at second layer, defects at the top, defects at the third layer. First two layers will be getting added up here. By that way, you can get the defect concentration, something like this. And we have studied say some choice state dependence of oxygen dimers. Say between oxygen dimer 1+ and oxygen dimer 3+, we see that oxygen dimer 3+, it penetrates deeper compared to oxygen monomer. This thing from the defect profile we extracted. And here, if we take indium gallium arsenide on gallium arsenide, this is indium signal, and this one is gallium arsenide. And can I take another 5 more minutes, please? As such,
continue. Yeah, I think it's good. Continue. Yeah.
Here we can see, and as such, what we do is this we have channeling as well as the random spectra, and this spectra we take at different energies, and as such, for finding defect density using dechanneling, this expression is this nd equal to this slope of this curve. Okay, dechanneling parameter is given by this expression 1 minus chi d by 1 minus chi v log value. This is dechanneling fraction. This dechanneling parameter as a function of energy it takes, and this one here we have plotted e power 0.5 versus dechanneling parameter, and here you can see linear. Okay, that means that for dechanneling parameter is proportional to e power 0.5, so defects are dislocations, and from the slope of the curve we can find what is the dislocation density. Okay, for indium gallium arsenide with different thicknesses, we have done this study at for implanted as well as unimplanted samples, and energy dependence, it is something like e power 0.42. Okay, it is dislocations, and the dislocation density is something like 4.64 into 10 power 5 per centimeter inverse. And as such, in iron crystals, we have implanted iron, and we have implanted self-ions as well as oxygen 18 isotopes, and in those ones we have studied the strain measurements. If you plot this dechanneling probability nd by nd sigma d with respect to e power of, we get linear curve something like this, and then you also see some sort of a flattening. Okay, some saturation. If this sort of thing happens, it means that the defect is not a simple dislocation, it forms some sort of a dislocation loop. And this transition region here, in this case it is 2.3 MeV, and from this transition region where you are getting saturated curve, from that one you can find what is the radius of this dislocation loop. And in this sample we see that dislocation loop diameter, the radius is something like 20 nanometer. And in the case of gallium nitride, we have seen this defect dependence, and in samples with when we grow the sample of gallium nitride with indium, we get something like e power 0.27 or something. It means that there are dislocations as well as stacking faults. while when sample is grown without indium, there only stacking faults are there. So there is no energy dependence. And we have studied this oxygen lattice position in BCC ion. And if you see this body-centered cube, the impurity, if it sits at this phase center here, you can imagine some octahedron around it. Okay, top with respect to this body center, if you draw here, you are having some curve. Here another this thing, it forms the octahedron. So that is octahedral. And go to tetrahedral. Tetrahedral, it is in same plane, but along this 110 position, it will slightly moved. Okay, and if you see this octahedral position, there are 6 octahedral positions. Okay, tetrahedral means in each phase 4, so 6 into 4, 24 tetrahedral positions are there, and as such, depending upon whether it is sitting in octahedral or tetrahedral, this oxygen tilt angular curve will have different shapes. For example, for octahedral, along 100 direction, we should get curve something like this. And for tetrahedral, it has to come something like this. In our case, whatever we observe, it is tetrahedral, and we get the shape like this. And this shape we can simulate with the Flex software, and we can exactly tell what it is. And for looking at this is signal from this RBS from ion. Oxygen is not visible. For looking at oxygen, we have studied nuclear reaction analysis in situ, and this oxygen intensity of NREI is plotted here. And with as such, when some defects are added, either in some cases we have interstitial dislocation loops, in some cases there are vacancy dislocation loops. So depending upon that lattice position is different, and that gives different shapes for oxygen. Okay, these shapes we simulate, and for example, in the first case where oxygen is at tetrahedral, and it is a point to position with respect to point to axiom displacement. We Flex software, and we put in similar structure, and we find that 0.37, and from that on we that this lattice position is whatever it displaced by point to axiom. It is due to the presence of vacancy dislocation loops, and okay, this position, and DFT is showing similar. We can compare experimental value with simulated value, whatever it is, and similarly like polarity we can do, and clean surface we can study, then hydrogen absorption or surface melting, and transitions they affect the that is charge density per unit length, and also in superconductors, if we see at low temperatures, lattice vibrations will be less, and as such, with the decrease in temperature, amplitude is going on. When you get that temperature, it will be reducing drastically, and from that point of view, for example, in OIBC, you know that there is coupling, the coupling is responsible for this sort of reduction, and Now coming to the conclusion.
I think there is some network problem. So we hope that Dr. Sundaravel will join us soon.
Sir?
Sir, I will try to contact him through his mobile. Okay, please give me some time. Unfortunately, Dr. Sundaravel's internet connection is down, and it is not clear whether it will be up any soon. So
we can take a 5 minutes break before Ambuj sir stop.
But before that, we will thank Dr. Sundaravel for presenting this very informative and illustrative talk. He covered so much in detail about the basics of channeling and also gave us so many examples. So let us thank him once again. Okay. So as Indra has already told that we can take 5 minutes break, and we start the next lecture at 11:53. So, okay. Thank you.
Seth?
Good morning, Professor Marshall.
Good morning.
How are you?
Fine. Sorry
Bit early for
next
you?
week. It's okay, yes, but sorry for next week.
Oh, it's okay.
I'm not.
We will
I'm
try
not
to manage.
available.
But anyway, we will miss you.
Yes, I know. Sorry.
Seth?
Yes.
Hi, morning.
Hi, morning, Ambuj.
Seth?
Yes,
Is
sir.
it visible? I was just sharing.
Yes, sir, your
It is
presentation
visible,
is
but not in
visible.
full
Just
screen.
now it is not in full screen mode.
But it
Okay.
is in, yes. Not full screen, but it is in, yes.
Yes.
And
It
you
is
should
visible
take,
now?
yes, but you
Full
should
screen
take out the right part.
Right one you cross it, sir. Cross.
But
Properties से cross कर दीजिए.
it
Yes.
is not in the full screen mode. That means.
Still, it is not in the full screen mode.
Okay, why it is not so? Okay, let me try in the settings.
View.
Okay,
Go to view.
it's
Full
not
screen.
activated in
Sir,
that.
I think it must be in full screen. Just see some other window. फुल स्क्रीन वाला विंडो पीछे कहीं होगा आपके बैकग्राउंड में.
अरे डबल ओपनिंग है क्या?
तो आपने जो विंडो सेलेक्ट की होगी उसमें फुल स्क्रीन वाला विंडो चूज कर लीजिए. It is already saying that it is somewhere it is slideshow is already there. So you press Alt tab and see if that full screen window is open somewhere on your PC. Alt tab. Press Alt tab. It will tell you how many windows are open on your PC, and then you can select that one. Click on that.
No, actually, let me just close what I was.
Close करके दोबारा कीजिए मेरे ख्याल से.
Yeah, so maybe. Huh?
Please exit from slideshow and let us check whether setup is right or not. There is an option to set up slideshow. Sometimes it is selected for a small window.
Okay, let me stop.
After you exit from slideshow.
Okay, let me just slideshow से exit कर जाए. Then I have to close it. फिर नहीं open हुआ तो close करें?
Yeah. No other option.
If I close it and it doesn't open. And let me just see in that slideshow settings. Something is wrong with the settings.
It's not highlighted now, your slideshow option. So that means it is already in slideshow somewhere.
Sir, why don't you use Microsoft Office?
I think it is open somewhere. The slideshow window is also open somewhere.
Sir, try opening in Microsoft Office.
Okay, let me try another thing. How do I stop sharing it? Okay, so I am stopping presenting. I am trying to do it again. Let me say present now, a window, and
Good.
is it doing the same thing or doing something different?
So far it is the same thing.
Okay, so this doesn't help.
छोटा हो गया सर और
Okay, let me close it and
work, no? Then you can send those slides to me, then I can present from here.
okay, let me just close it once and then open it again and then see.
आपकी कोई एक दो फाइल और खुली हो तो वो बंद कर लो, भी टाइमिंग बाद में खोल लेना।
But you can make PDF and then present from Acrobat.
Okay, because it is, let me just find out here.
हाँ बंद रखना है ना, क्या बंद रखना है?
ये तो क्रैश ही कर गया एक्चुअली उसका this program has crashed actually, so let me just give me a couple of minutes more, so let me try to find out the file. वो impress में जो खुला हुआ था it has totally crashed, so
लैपटॉप में कर लीजिए ना।
एक मिनट।
So I am trying to test again. So let us see if it works now. तो कुछ हुआ? सैफ?
हाँ सर, अभी आ गया। Research, ion material science research activities at IUAC.
तो ये
still not in full screen.
अभी
सर कोई बात नहीं, अगर आप इसमें स्विच करके दे पा रहे हैं ना स्क्रीन, मतलब वो चेंज कर पा रहे हैं तो इट्स ओके।
Sir is trying, no? Yeah.
अभी क्या हुआ?
आ गया।
अच्छा, now the problem is, so I cannot see it, so let me see if it is changing the screen.
Yes.
Okay, so then I cannot see it. So if there is any problem, somebody has to call me and tell me.
Sir.
We'll tell sir.
We'll tell sir.
Okay, so if
So
there
we
is...
can start.
So participant, by now you know that next talk is by Dr. Ambuj Tripathi. He did his MSc from Allahabad University in 1985 and PhD also from the same university. He joined IUAC in 1988 and he is presently scientist H in IUAC and he is program leader of Material Science Group, ECR based LEIBF group and Radiation Biology group. He has played key role in the setting up of various experimental beamlines and various in situ online facilities at IUAC. His major interest lies in ion beam induced modification of carbon-based 2D materials and nanostructures, ion beam induced modification of surfaces and interfaces, and synthesis and characterization of nanostructures. He has published more than 200 papers in journals. And today he will be describing what are the research activities, what type of research activities exist at IUAC in material science field. So, sir, now you may begin your presentation.
Okay, thank you. So, Dr. Saif, since we are from the organizing committee, so I don't think I should have been introduced, but still good. And for the participants, what Saif was trying to tell is that I am too old. So that is why he mentioned that I am here since 88, so almost more than 32 years now. And what I am going to do is to give you a brief thing about what we have been doing. And I should emphasize two things in the beginning, that I will just give some of the areas and I will mostly just cover some of the things which I have been involved in. And you have to look into the site because almost all areas of material science are being followed here, and different people are expert in different field. So just don't go by what is there. You have this our home page site, so details, if you go there you will see all the areas. So and as I start, the first thing, this plan of talk, as I said, I will just give a little of brief and some of the facilities, some of the results. And one thing which I thought just in the morning I added this. If you remember in the first talk when our director was mentioning, it talked about this ethics. Nowadays it is becoming very important. So I just want to add up that whatever I will present, this is the work of a lot of people. And that is why, because I may not be able to acknowledge everywhere. So these are especially for the school. So work for different researchers are included. I have just tried to restrict it to my people, to the results where I have been involved. So I think almost all the results you will see is where I have been involved, but there may be a few where other people are there, and then I have forgot to mention in the slide. So just take it as information and not the individual things. And this is also is a very, as I said, those who have attended some of these talks earlier should excuse us, because we always go by that there are new students. So this is taken into view this, and a lot of things which are very common. But since it is the end of the school, I think all these things you are familiar with this, that we are using these ion beams for all the three categories. We use it for synthesis, for modification, and for characterization. These are the three areas in which it is being used. You have heard almost all the things as most common ones, which started with this origin of this materials characterization is this RBS, which you had a separate talk on that, and so which works in the few MEVs. This marker is visible there, no?
Marker. No. Sir, you just move your cursor.
Is it cursor is visible?
No. So you try to right click and see if you can find something.
No, okay, so let's leave it because it was in that as soon as you go to full screen mode, it disappeared. So I think it was visible only in that mode. So the marker is not there. So I will just say what is the main thing. So if you look in the characterization in few MEV, the RBS, that is the maximum thing which are used. Most of the work what we do at IUAC comes under this materials modification, where you have again the two ranges. By now you are familiar when we talk about lower energies, we say this is the nuclear stopping, and when it is at higher energy, we call it electronic stopping. The difference is where you have whether the collisions are elastic or whether the collisions are inelastic. So inelastic, what happens is inelastic, this is a simple, you can say, momentum transfer, and then this leads to atom displacement, and defects are mostly will be point defects. And mostly we talk about lower energies. Lower energies means of this order of few tens of hundreds of keVs, where this elastic collisions will dominate. And as you increase the energy, if you go on the higher energy side, which is on this right one, you will see electronic stopping. Here the inelastic collisions will start, and then there will be atom excitation, ionization, all these processes will start where electrons are getting excited, or so they might be the different processes which you have heard in the talk of Professor Marcel Tulemon, who is fortunately sitting here. So all those things are calculated. You can see what is the electronic temperature, how it rises, how it falls, how the tracks are formed. So all those things which come into that. So that is where the columnar defects things into come. And as mentioned, it is goes on the higher energies. This is again a very common curve which we always show. All you have to see is here is on the top there are two regions are written, Sn dominates, Se dominates. And if you look in the energy scale, it says somewhere around 1 or 10 MeV up to where you see the purple curve, which rises. So that gives the nuclear energy loss. So it rises up to something around a few of MeVs, and then it starts going down. And electronic energy loss, which is shown in this as Se, E for electronic, that it starts increasing somewhere around 10 MeV or so, and this will reach a peak of in the range of 1000 MeVs or hundreds of MeVs. Of course, this plot, what we always show, this is stopping power. This is for a one particular ion beam and particular target. So these combinations, it will keep on changing, and this will the actual values will change for all the different systems. But overall, you can say at somewhere in the order of few hundreds of MeV, this peak will come, which we refer to as a Bragg peak, and then this will also start going down. So these are our main areas where we work with. And these are the three models which thermal spike is already the mostly what we use. So all this has been explained very nicely in the talk, so I will skip this part. But this is where you say that how it is heat, this temperature rises, this electron temperature, and how the heat is taking away. Mostly this you have heard in the talks now by this, the role of delta electrons and how the temperature rises in the picosecond time scales, and then energy is transferred to the lattice by electron phonon coupling by those the coupled diffusion equations what is covered. So all that this happens, and then you reach to the your material. One thing I just wanted to emphasize, two words which we always use. As you see, when we have this school and conference, we always refer to it ion beams induced materials engineering and characterization. The slight difference when you use the word engineering instead of modification. Modification is you have bombarded and then this something changes, so you study it. It may be desired. When you have a desired property and you work towards that, that is where the word engineering comes. And this is where we use the word engineering effect. So you need, what are the tools here? The two tools which you use here is the energy, how you select the energy by ion mass and energy. You have this electronic energy loss. So AC, that becomes your, which will decide what type of defects take place, and the number of defects what you are trying to create will depend on the fluence, how many ions in per centimeter square this is being used. Other definition which we very commonly use is shift heavy ions. This the conference which will start in a couple of days. Earlier we used to call it SHIMAC, so shift heavy ions in materials engineering and characterization. So what is the shift heavy ion? This is where the velocity is equivalent to electron Bohr velocity. This typical energy, as we mentioned in the last slide, it's something around 1 MeV per nucleon. And here this electronic energy loss dominates. You always remember, if you see the curve earlier, that whenever we say it dominates, it doesn't mean that nuclear energy loss disappears. So that also remains there. But electronic energy loss value keeps on increasing, and that is where this dominates. And as I mentioned about the conferencing, so SHIMAC, to which changed this name to MI, because we also started including lower energy. So basically you are looking at the complete range of things which are happening. So this is the two basic things, the word which we use shift heavy ions, and this engineering where we use the engineering. So these are the tools by which you can engineer the material. And we have a large number of facilities. So I have in next of the slides, for some first 8 or 10 slides, I will cover the main facilities which we have, and then I will come to the one of the programs what we have. We have among the major facilities, we have as ours is the accelerator facility. I will show some of those things in the next slide. So we have 2 experimental beam lines, which I will show in the next line. We have different irradiation chambers in those lines. We have a lot of in situ and online facilities. What is we refer to in situ and online is, you see, whenever you are doing this irradiation and then you are doing some modification and you want to study it. So a lot of time what you do is you say mount 4 or 5 samples in this what we call the sample ladder, and then you irradiate them at different fluences, and then you take it out and do the characterization. Suppose you have 4 samples done at 4 fluences. But sometimes this question will arise that how you are sure that initial conditions of the 4 samples were same. So if you can afford to do it, if you don't have too many samples, if you have very well want to do a very precise measurement, what you would like to do is you would like to do this irradiation and measurement on the same sample. So what you do is you irradiate it, you do the measurement, increase the fluence, do the measurement. Those type of things we refer to as in situ. So like we have this in situ XRD. So XRD and Raman we have mounted in the beam lines. So there you can increase the fluence and look at the XRD and Raman after this. A similar technique what you saw, you heard the talk about RBS. So there you do this again mass, you can do the depth analysis, how this which mass is at what depth. The similar thing you can do with ERDA, and when you are doing it, this is an online, we refer to as online ERDA. ERDA is some sort of a complementary to RBS. Both things will give you the same elemental depth analysis. But RBS, as you know, you always say the lighter projectile, heavier target. So you need to, because you are looking at back scattering. So by principle, you cannot do very light elements analysis using RBS. So for that, you have this technique ERDA. So very major requirement will be if you want to look at in the hydrogen, because there is nothing lighter than hydrogen which you can do RBA, so you always do ERDA for that. So that online ERDA, and then we have binaural distance also in situ available. There are a lot of offline systems. I will just, as I mentioned, show you some of the slides just for showing the systems, not going into much of the details. We have optical measurement. We have a very active group. This FTIR, UV visible, NIR, and this spectrophoto. This is spectrophotometer. We have a very major transport and noise measurement setup. We have lower temperature magnetotransport with the Tesla. And in surface this microscopy, we have SEM, we have which has all these modes, SEM, AFM, MFM, all those things. We have a scanning electron microscope, and besides this pelletron and higher energy, we also have some very lower energy things which are for low energy radiation. We have two facilities. I will show in the next slide those things. And for doing any of these things, you need basic sample preparation techniques. So we have electron beam evaporation system, RF sputtering, atom beam sputtering. And for going into all that, whatever you need is ball milling, furnaces, box furnace, tubular furnace, and all that is there. Okay, so these are, we say this is the main this accelerator facility, and we have different type of accelerators. The first main our facility is this pelletron accelerator, that is name is called 15 UD pelletron. So that is the main machine what we use. And then the beam accelerated from that can be further accelerated using LINAC. So you see in the center of this top hub what we called this LINAC. This is the linear accelerator. This is niobium QWR based this cavities. And in beam hall 1 we have facilities, and then this is accelerated through this superconducting LINAC, and then the beam goes into the next experimental hall, which we refer to as beam hall 2. So we have one beam line dedicated for material science in beam hall 1, and one dedicated beam line in beam hall 2. So these are the two material science beam lines which are there. And you heard this talk about RBS. So on the right side you see this is this RBS facility, which is based again on this 1.7 MV accelerator. And on the lower side you will see we have two, this ECR based and SNICS based. ECR is this which gives the positive ions. So most of the inert gases, etc., if we are doing, so all those we have it what we call low energy ion beam facility, and this gives the positive. The other one which we have is then SNICS based. So that SNICS source is the source of negative ion by cesium sputtering, that gives negative ions. So that will be the negative ion facility. Roughly you can say that positive ions you will use mostly from LEIBF, and metallic and some of the things where we cannot get this negative ion, all this you will use the ECR source, like argon and krypton and all those beams. This, if you want to use, you will be using this facility, because pelletron also uses, by the way, SNICS source, so you don't get this inert gases, this ion beams from there. So all that you will have to do from this ECR based source. And SNICS of course is the same what is used in pelletron. So if you want to go to the lower energy side, few hundred kVs to a few MeVs, you will be using this facility. We had also developed this bottom right corner. This is what we say 50 kV accelerator system. We also have been developing this tabletop, what we call tabletop accelerator. So there are two already available in IUAC in this kV energy range. The idea was to look at the systems which can be given in the labs and for master's level program. So some of those universities have taken this design, and there are vendors who can make it. So that is being encouraged. And one thing which I have not discussed till now, which I was skipping, we also have this AMS facility. So that now has become a separate area. But some people also say that it should be included in material science, because but that is a different type of analysis. And we have a whole group of geochronology. They have a lot of facilities which we mentioned in material science. They are also use the similar facilities. So they also have a lot of this offline characterization tools. Now coming to showing some of these photographs. So this is the this is the beam hall 1, where we have this is our sort of a workhorse. So on the left side you see the chamber, and this that is what is our main irradiation facility. So that is in the beam hall 1. It has this is a sort of overview. You see 3 chambers, and if you look at closely, the first one is as I mentioned, where maximum irradiation will take place. So that is in the beam hall 1, and this chamber has where you can do the irradiation at liquid nitrogen temperature, room temperature, and high temperature also. This is where we also have the setup of doing this online ERDA and this transport measurement, etc. online. Okay, the facilities are can be used in this chamber. And ERDA, this is a small this just how the detector works. So I will skip this. This is not very important here. And this is the other this quadrupole mass analyzer. Once you irradiate it, if you look at what are the masses required, so this is a system which can give you the details of the mass analysis of this whatever comes out of the setup. So as I mentioned earlier, from this irradiated beams, then goes to the quarter wave based LINAC, and then it goes to the beam hall 2. This is a schematic on this, and as you see on the right side, something around what you say 15 degree on the left side minus 15 degree is the material science line. This is the line in which we have again 3 chambers and these 2 major in situ facilities, in situ XRD and in situ Raman are mounted in this beam line. So this is the beam line in beam hall 2, what we say where this accelerator beam through the neck can go, and then it is the irradiation chamber. The same similar to what we have in beam hall 1. So here you have a similar sample ladder. Whenever we say this ladder, we generally this is a sort of a arrangement on which you can mount more than one sample at a time, because whenever people want to do different samples at different composition or something, you have what you want to do at different fluences. So then you can do in then it matters how many samples you can do at one time. So we have 4-sided ladders, we have 6-sided ladders, in which you can typically more than up to 20 samples to 30 samples you can mount at a time, so that you don't have to take it out after irradiation and break the vacuum every time. So then some other common things, optical microscope. This is the motorized movement. We have this is what I mentioned is again one of very widely used systems. So this is a FESEM, this scanning electron microscope. We have atomic force microscope. Again, combined between AFM and SEM, you can do most of this characterizations you can do on the surface. And very sophisticated thing which has added in this microscope series is this transmission electron microscope, which has this is the GOL 200 kV, this JEM F200 system. So this is also now operational, and it's supposed to get a lot of this EELS setup will also be active with this. Actually, when we are talking about SEM and this, sometimes you have insulating samples which cannot be done very well by this where you are using this electron beam. So you need some time to have a conducting layer. So this is the coater we have for that purpose. Another facility which is looking at the surface property is this contact, what is a contact angle measurement. So this you must have read about this where you want very hydrophilic or hydrophobic surfaces. They have different applications. If you want to look into all that, you have these facilities there, so you can do those type of measurement using the how much time I have this 12:45. Okay, yeah. So and this is used for, so contact angle measurement is basically once it will tell you whether when something falls on a surface, whether this like droplets you must have seen on the this lotus leaves, so it doesn't seal, it remains like a bubble. So whether it is going to stick to the surface or whether it is going to stick at bubbles, all this is decided by this type of measurements. Where it becomes important, as I said, if you want to have some surfaces like if you're looking at the windows, you don't want something to stick there, then you need the different type of contact angle measurement. It should be high so the water droplet becomes lots of rolls down and doesn't stick. On the other hand, if you want to have something like a paint which you want to spread very uniformly and get stuck, then you're looking at the other extreme of the contact angle. So all those type of surface properties you can see. This is the NC2 XRD, as I said. The beam comes from the right side and then XRD is mounted. So this is a conventional XRD system which has been connected to the beam line. Similar thing is with this Raman chamber. So this is the I have shown this slide. You can see this is a special chamber which was made for this purpose, so that you can take the probe closer. So this is a sort of a half semi-cylindrical surface. And in the in situ series, we had tested this in mock setup in this. And coming to some of the offline facility, this is the UV visible NIR spectrophotometer. As I mentioned, we have a big this low temperature magneto setup. Also, we have this this thermoelectric setup. So all those things with the different ranges and with different magnetic fields, you can measure the properties. So this, if you had come to IUAC, you will see there are 2-3 labs in which we have in transport, what we refer to as transport lab, where you can do CV, IV, noise measurements, and you can do at low temperature, and you can do it in magnetic fields, and this, as I mentioned, this thermoelectric setup. So these are the thermopower setup. So these are these 2 different labs which go into this transport lab, and they are taking all sorts of measurement are possible. Coming to this this low energy ion beam facility, as I mentioned, these are the separate accelerators. So this is where you can do this few hundred tens of few hundred kVs to few tens of MeVs, and that this is an ECR based source. And this is the RBS facility which we showed. This is again a Photoelectron, much smaller than this. And for preparing samples, these are this sputtering setup and this atom beam and RF sputtering setup. One other system which had been very widely used, and you will find a lot of measurements done, is using this. This is a very small setup where you could do this co-sputtering, and here you can get this atom. We call it atom source because you can get this neutral atoms, and you can, most of the other things which we have been showing, you will get this either positively charged or negatively charged ions. Here you can use this atom sputtering, and then in the target and the matrix you can make this co-sputtering setups you can make. So these are the different facilities. So since I'm reaching around 25 to 30 minutes, in next 15 minutes or so, I will pick up some of the examples. And the examples where we have used these facilities and some of the interesting things which I find interesting. So this will be common thing. So one area where which we have been using is for nanostructuring. So some of the examples I will show you is what we call these modifications of surfaces at the nano level. But there are many different areas. So this is a sort of gives a summary of different areas. So as I mentioned, nanostructuring, so this is one part of it. So that is the first one. You have heard a lot in this school about this ripple formation. So different people have done. So that has been covered. So here, this is one example I have given, but this work has been done on all the, you will see the results on silicon, you will see the result on germanium, you will see the result on this different carbon based surfaces. And among the simulation codes, this Dr. Hossas made this SD trim using SP. So these are the modifications which we have been done. So there are this band gap tuning, resistive switching, this core shell structure for hydrogenation properties, annealing stability in graphene oxide. Some of these examples I will pick up in the next slide, and some of them I have just listed. So nano composites and applications, this novel phase formations. In some of you who will be attending in the conference, you will see some of these topics being covered there from the specialists. And electronic sputtering and beam mixing. So some of the recent work which was done in tungsten and silicon multi-layer. So if I have time, I will go to that. And then in semiconductors, these are the general areas I am just writing. And what I will suggest is, if you go to our site, you will see all this, whatever headings are given here, you will find in our home page. Details are given for all of them. So those write-ups have been prepared by the experts in different areas. Like if you are looking at this thermal, this luminescence and transport measurement, there is a section on that. If you are looking at this optical properties and this TCOs and this all those things, there is a separate page on that. If you are looking at nanostructuring, there is a separate page on that. I have mentioned this carbon-based materials, so there is a separate page on that. So all those details with recent publications. So you will find the areas of research. You will find the detailed work, summary of work, what is being done, and the list of publications. So I will suggest you to go to the pages and see it. So I will just some of the examples I will pick up. I always start with this slide, which I have always found very interesting. This is what we had done at IUAC, looking at this carbon. You know, this simplest structure is this HOPG graphite. So this is what we were looking at the surface. Why I always mention, I find it very interesting, is that by the time we were doing our post-graduation and graduation, we generally used to study that you cannot see this type of structures because this carbon atoms sitting in this hexagonal lattice, because resolution at that level was not available at that time. This was one of the first images by the person who discovered scanning tunneling microscope. He got Nobel Prize for that. But we could once we could do it here. We finally had a homemade STM, and by which this image we could look using that. So using a you can get to see the carbon atoms even with a homemade STM. So the technology developed for now, they are commercially available. Once you understand it, as I mentioned, you can even make it home. So this was always find it as an interesting image to show. So this is a carbon atom. At that time, what we were doing was looking at the conducting track. So this was one of the earliest work we did using one of this attachment. This is with this commercial, what we had this atomic force microscope, which I showed you. So there's one of the modes there is which is called conducting AFM. So this is a tip which you magnetize it, and besides looking at the surface topography, you can also look at the if some of the portions are irradiated. So this is the work. Was continuation of some earlier work where we had seen that the surface become more conducting after irradiation. So we were trying to understand it. We were trying to see whether we can see it in this conducting portion. So wherever ion beam had hit, so what you are seeing, those bright marks, these are the where the ion has passed through and has changed the conductivity. So these are basically the bright spots are the higher conductivity, and the overall black background is C60, which is supposed to be insulating. So wherever ion beam is hit, it becomes as conducting. And one important thing is you will see this fluence here. It is written 2 into 10 to the power 10 per centimeter square. Whenever you show this type of results, always the question will come is that how you are sure that this is because of the ion beam track. So what a very simple way of doing it, you correlate it with the number of impact. So if you increase the fluence 10 times, you should expect this number of tracks to go down, to increase in the number of fluents. So as you can see in the two images, this is one is done at 2 into 10 to the power 10 ions per centimeter square. The right side image is done at 2 into 10 to the power 11. So you do 10 times higher, and then you expect this to be 10 times higher, the number of impact, these bright spots you are seeing. And if you are doing, then you can do this characterization on that. So we looked into this, we did IV on that. So that was one of our brilliant PhD scholar who had worked on that. So that was this was part of thesis of Dr. Amit Kumar, who did PhD from here. So this he did measure this IV VI measurement, I should say. This contact, this is because this measurement is you apply voltage, you measure the current, and you see that if it is less insulating, conductivity should be more. And if you are saying is that it is related with their electronic energy loss, so these are the type of experiments you do. As you can see, we have taken 3 beams, 120 MeV gold, 190 MeV silver, and 55 MeV titanium. What varies is in the next line you see the electronic energy loss value. So which is around 1300 in the first case, 1100 in the second case, and 500 in the third case. So you vary electronic energy loss, and you see if you're saying it is conductivity is because of this SE value, then it should vary with that. So as you can see, the threshold from where the current starts, this black, red, green, and this blue curve. So you see as you increase the electronic energy loss values, the value at which this current starts coming decreases. So that means it is becoming less conducting. So you can draw this. You can also measurement its field emission properties. So that was all done. So there are 2 different this Journal of Applied Physics paper on that. So that was the first one on which this conductivity part was studied, and here the field emission part was studied. And all those measurements are possible which can be done. And why I wanted to show you in this is that this is something now we have extended it to, and there are a lot of field emission applications for if you are working on say in satellites, where some of the things where it becomes very important for initial starting of currents in some type of detector. So we have nowadays we have a project on which we are trying to see how this field emission properties can be enhanced, which becomes useful in different type of applications. So it is a very important study. This was done in IIT Delhi, and the project I am referring to is with IIT Delhi, and one of these labs in UK. So in United Kingdom, one of their space labs. So we had a project on that, which we have been trying to look into this. And the similar thing, so you heard this talk of Dr. Rahul Singhal. So this is a part of his work. As I mentioned earlier, I don't see the reference written here. So some places we had forget to write it. So this was part of his work. So C60 was Amit's work, and C70 was Rahul's work. He had done these measurements. Again, you can see that there is insulating, where the ion beam is falling, the part becomes more conducting, and again you can do this ion beam measurements and things like that. So conducting tracks is these last two examples I showed you was where you can see this increase in conductivity. So both these measurements were done with ion beam. And the one other area which you have seen a lot in the conference is ripple factor. So I am showing is one of these initial works which we had started. Again, if you see at the energy, this is done at very low energy, and this is one of this this small machine you can do. Why I am showing you is that you can see that different energies you can do different type of things. It's not that you are limited to different what you can do. Of course, we try to focus is in our pelletron, which is our main facility, but you can do it at a very lower energy. And this is part of Dr. Indra's work. So this also, she extended it, and a lot of more work has been done after that. This is one of the older slides. In the beginning, what we had done was, and so that was done, and you see on silicon, earlier example I showed you was germanium. It is indium phosphide, and then one of other scholars did it on silicon carbide. So that was one of the research scholars here, Ishpal Katharia. So he worked on this in silicon carbide. So this are shown in a different energy ranges on different type of surfaces, and then of course all this adds up to your knowledge. So this is a very major activity. I will slightly shift from here, and next 5-10 minutes I will just show you some of the examples on the 2D materials. So we had also started some measurements on carbon-based materials. So this was one of research scholars here, Dr. Sunil. So that was part of his thesis work. So here he had looked at the graphene. So here, first image I am showing is here we have tried to look. This was done by the cleaving, so it is not a perfectly uniform film. So some places you have graphene, some places you don't have. So this is transferred from the earlier very first example, which if you remember, I had shown was that HOPG. So this, if you take a layer of that HOPG, this highly oriented periodic graphite, a single layer is supposed to be graphene. So this is what it is there, but once you transfer it, take it out and transfer it on this, it will not be uniform. Some places it will be there, some places it will not be there. Some places it will be one layer, some places it will be two layer. So you try to find out which are the areas which are single layer, two layer. So of course you always get this idea from this looking at even with an optical microscope, you can see with this color, so that gives you an idea. But this is an AFM image, so this is actual measurement of the thickness. So here you are trying to see the height of this, and as you can see, this thickness generally varies. Each layer is around 0.35 nanometer, so 3.5 angstrom. But the very first layer will be, because this is between the substrate and the surface, so that is it starts at around 6 or 7 angstrom, so 0.6 or 0.7, and that is how you can get this number of layers. So you can see it, you can find the samples, and then you do this irradiation work on that. So what after irradiation, what happens is that we go back to this thermal spike calculation. And if you remember, I had during the school time, I had raised this point, and a response was given, because whatever we do, this calculation, thermal spike, etc., that is for bulk, but we had also tried to use this for this 2D materials, so in thin layers. And this is one of the example, again using this Professor Tulemon's software of this thermal spike. So that was plotted, and what we tried to do was we tried to define two temperature zones in that. So as you see, the temperature goes down radially. So somewhere in the core it will be very high, which will melt the lattice. Somewhere very far away it will be so low that it will not do anything. But in between there will be a temperature in where it can do the annealing. So means the temperature is above required for annealing, but below what is for doing this melting. So we had tried to use this model and try to get this radii into which this things areas can be fitted. So this was the work, and it was we finally tried to get this radius on that for the core radius, and this outside means this halo. So we gave this name core and halo. So we said the core will do the damage, and halo will do the annealing. And as you see in this first curve on the bottom side, initially this damage goes down. The right side, what you're seeing is these are the Raman. So if you look at the first peak in this Raman spectra, there are three peaks which are showing D, G, and 2D. And if you look from bottom, which is the unirradiated, and go towards the top with increasing fluence, so you will see this D peak in the first three cases slightly goes down and then increases. So D peak generally refers to what we call this, it relates to damage, and this ratio of these two will tell you whether the damage is increasing or decreasing. So as the D peak increases, that is what is plotted in the left side curve, and you can see that initially this goes this annealing happens. So damage disorder goes down and then it starts increasing. Our explanation was that initially this halos overlap. So initially annealing happens and then gradually the cores start overlapping and where the damage happens. So these are how it was done. So you sum these results. There are 3 papers. So one is this on this nanoscale research letters. Then it was further extended, and this was in the applied physics letter. So this is all part of Sunil's thesis work. And here we also did that XRD. Again, XRD, you will see that problem is that if the intensity is very low, this will not show in normal XRD. So you need XRD this synchrotron XRD for that. So this measurement was done in the synchrotron at this in Japan in KK. So then you do with this measurement and try to fit this. So this is all done in a series of paper where we did this measurements on graphene. And as I said earlier, that whenever you say this is because of ion beam, you always have to show that this property, if you are saying, is because of ion beam or because of electronic energy loss, it should vary with this electronic energy loss. So then this measurements were repeated in again 3 energies. You can see 60 MeV titanium, 100 MeV silver, 150 gold. And if you look at the SE values, for titanium it is around 7 kV per nanometer, for silver it is 14 kV nanometer, and for gold it is around 20 kV nanometer. So 7, 14, 20. So we tried to go into 1:2:3 ratio and did this measurement and try to show that this can be correlated with the value of SE. So this was that measurement on this. So I will a couple of this I will skip, but just to mention that we also looked at this charge neutrality point and some of the things. That was a third paper which I am not showing here. That was in Journal of Applied Physics. Some other interesting thing which was we had done was this was on the core shell bimetallic structure. So these are the SEM measurements where you can see this core and shell. And then we had done this measurement. So this is this SEM measurement. With SEM, you can also do this elemental analysis. So you can show what is the core part, what is the shell part. So you can do the analysis. And similarly, this cross section. So these are basically trying to do this is cross sectional. You can also do these measurements if you can cut your sample, and like in TM, you must have heard about this cross-sectional TM. You can also use to try it with the SEM. So this is one of the user sample from Agra. So they had done some measurements here, and this is done. You can do this cross-section measurement and look into this elemental analysis. And where you can do at different levels that this is on the ITO substrate, then there's a zinc oxide layer, and then there's a copper oxide layer. So you can do all these measurements and see. The main idea was that they were trying to look into how this presence of whether there is any oxide phase at the interface or not, and whether, because you expect it not to happen. One other example I had just thought I will show you again a similar measurements which was done on this mixing. So that was one of again scholars. This is Sashti. So that was which is so all these different type of measurements you can do at the surface and how the structures develop on the surface. Since I am falling short of time, I will quickly just skip through a couple of them. This was one of the users, Mr. Jayaprakash. This was part of his work. So there we were trying to see on the surfaces how you make nano structures on the surface. So this was a gold thin layer, and then with irradiation, and you can make this nanoparticles. So on the lower side, this is the this central image is the TM, where you can see the circular nanoparticles. And as you increase the image, the last right side bottom, you will see that they are getting elongated. So you can also do the shape engineering. So you can make nanoparticles on the surface, but you can also change on the surface. You can do on the embedded. And when you are doing all this analysis, one slide I sometime include to show you that this is interesting, just to show that in FM and SEM, if you look at the same thing, you will find that sizes are different. So these are the measurement techniques, what you measure with different systems. So you will see how the size distribution, if you see FM is showing a slightly higher, the same sample is studied with FM and SEM. So those are the about the different techniques. So you have to always keep in mind that all these measurements when you are doing, so you should know the limitation of this technique which you are using, because what you see may not be exactly what is there. And about this again, this nanoparticles on the surface, as I said, if you are seeing with ion beam effect, you should be able to do with the different ion beams. So this was on gold, this irradiated with 150 kV organ. So another with 150 kV organ done on done for the silver nanoparticles. So that was shown on the PVC. So again, as you irradiate with increase the fluence 5 into this 3 fluences, 5 into 10 to the power 15, 1 into 16 and 5 into 16. And as you increase, this size distribution decreases and you can get this nanoparticle formation on the surface. This again was mentioned. The next example I'm going to say is again which was shown. So that is work of Dr. Saab, where you make the surface ripples on the surface and then try to make nanoparticles. You will see there is a very detailed paper on this which came later on. I removed some of the slides because I realized that I will be crossing the time. So if you are interested, so this was giving a glimpse, but 2-3 things which I just wanted to in the end I want to show. Some of these things you will find. There was a book written by Dr. Avasthi. This is a Springer series. So this is on with our earlier director, this Professor Mehta. So this you will find a lot of work what I have seen. So whatever has been done, major summary of that you will be able to find on that. And for making this sort of giving people a platform and getting all these discussions, we have this this school and conference. We, as I mentioned in the first opening session, that we do these 2 conferences, and we have every alternate year this SHIMAC and this nanostructuring. Earlier ones you will see the proceedings in radiation effects and defects. There were SHIMAC was in 2 of these special editions of this on the conference. This 2010 and 12 we had in this radiation effects and defects, and then a couple of them we had in this advanced material lectures. And so I will like to stop here, and this is one of this nanostructuring with ion beams. And this was we had done this Indo-French workshop, which again I mentioned in the opening session. We started before we started this regular series. We had one Indo-German, which is you will find this is this a separate again a special volume on that, and then this shift in the nanostructuring of the ion beam, that was the Indo-French, which we had published as sort of a book. You will find different chambers. So this was there with Dr. Avasthi and Dr. Pevin, who was from the French side. So I will stop here. And as I mentioned earlier, if you want any further details, you can write to us on the email. You can always go on the website we had recently updated, so we'll find most of the details there. And all of us, you will find the people's email details ready, so you're always welcome to write down. This proposals details, how to submit proposal, etc., is also available on the website. You can go on the website, see the user. So there is a user page. On this you will find how to apply for beam times, all that BTR, etc. You will find there the details given there. So all that you can find out there. So thank you for your attention. I will stop here. I would like to take a couple of questions, because we thought we will 12:45 we will stop it. So let me stop here, and there is a few questions we can take, or as I mentioned, otherwise if you are not there, we can always, you can write mails, etc., and discuss it later on. So thank you for your attention, and thank you for all of you attending this school, because this is what finally makes it a success, if people are attending and taking interest and taking something from here. Okay, thanks.
Thank you, sir, for covering the experimental facilities at IUAC and giving us a glimpse of material science research being carried out here. I'm not seeing any questions, sir. So
I would also,
question.
Yeah, so I would also be okay. There is one somebody saying somebody we should mail about getting beam time, sanctioned beam time. You will find all those details in twice in a year. We have this. If you go in our academic calendar, you will find what we call user workshops. So twice in a year we have that in August and December, where these proposals are given and submitted, and there is a last date for submission. So that is generally a month or so before that. So for December meeting, which is supposed to happen in a couple of weeks time, 10 days time, this proposals, I think last date was somewhere in October and or early November. So all those dates are given. This is the online form submission. Of course, there what you have to show is what is the important about the ion beam, because this is mainly an ion beam facility. Offline characterization, etc., and sample preparation is available to those people whose beam time is approved. And when the students are coming and when these people are come for experiments, we provide TADA, and then all the facilities are provided. Of course, nowadays because of this COVID, there are special restrictions, so you have to find out this is being worked out. There are different SOPs for that, standard operating procedures, but otherwise in normal conditions, all these people come, stay in the guest house, do the experiment, and if they want, they write for, like, if they want to do some characterization, of course they have to inform it earlier and book a slot, and then they can do this characterization, etc. Okay, there is one from Bhim Khan. He says, how will we select these Swift ions like silver, gold, titanium for materials modification? If you remember in these 3 slides, I showed you the value of electronic energy loss. So we decided by electronic energy loss values. If you have some theoretical knowledge or some published work, you can know the threshold. So for each modification in material, this below some electronic energy loss values, the change will not happen. In some energies, it will happen. So you generally choose the energies, depends on what type of measurement you want to do. So if you want to look at the modification, you generally try to be above that threshold. So you choose a beam and target combination, your sample combination, so that you are above that threshold, so that you can do the modification. And then this beams and energies will help you in varying this SE. If you remember that example I gave you in about this graphene, so these 3 beams which you have mentioned, that was to change the electronic energy loss value from 7 kV per nanometer to 14 kV per nanometer to 20 kV per nanometer. So then one of them was before threshold, so we showed that there is no change in that, and then the other 2 had changed, which increased with SE. So now you are sure, so you know that threshold. So we say this was below the threshold, so no modification took place. The other 2 were above the threshold, so the modification took place, and the modification increased with electronic energy loss value. So these are the type of studies which we will do.
Any other question?
Okay, so
let us
once again thanks, sir.
Yeah.
I cannot thank myself, so
So
Then now we
we will,
request you to share the next session, which is
Uh,
the final one.
sir, just we would like to thank sir to coordinate the morning session, and now we will be having this feedback session. Ambuj sir to coordinate.
Indra, you can just start. No issue. You just start. What we want to do here is just give this feedback. So you can. It will be better if some of you just write if you want to say something, so that we can call from that sequence. So just write your name and then you can say a couple of minutes. So just keep track of time. Of course, you are
Yeah.
free to say good things. Everybody likes to hear nice things. But if too many of you are saying that, so it doesn't help. So you can give
So
any positive
basically,
criticism.
feedback means how we can improve in future. Suppose such kind of school we are going to organize again for the benefit of students and participants. Then what should you people suggest? And please write in the chat box. I'll keep on reading. So Vinayak is saying, can we give feedback through email? Of course, you can always give feedback through email. Our school email ID from where we are communicating to you. So that is a good thing to do. Marshall sir is saying thank you for this interesting school. So we are glad that you could actually accept our invitation to deliver lectures for the benefit of students. It is a really very uh, we are very heartfelt. We are heartfully thanking you to accept our invitation. And any other feedback from student is welcome. Please write in the chat box.
If someone wants to talk, you can ask them to tell also.
Yeah, if somebody wants to speak, then also they can unmute and try to speak. Shiv-Kumar, school was very informative. Okay. I hope that you could get some idea about how you can choose the ion beam, and hands-on training might have helped you. SRIM simulation and RAM simulations. So any other feedback?
Good afternoon, madam. I am Dr. Srinivasan from President's College, Chennai, Tamil Nadu.
Good afternoon, sir.
The school was very successful, madam. I have learned a lot of things, especially from trim calculations. When I applied my AUC 69 project proposal, I do not know how to calculate the electronic loss and the nuclear loss. You told me to go to the website of trim and trim manual website and find out how to calculate the SN and the SE. And that time the software was not installed in my computer. So in this session, I learned how to calculate the SN value and the SE value from trim calculations given by the expert in the school. It is very nice, madam.
That is really nice to hear, sir. So
Yeah.
kindly you make use of it during your presentation. You will be defending in AUC. All the best to you.
Madam, one more thing. If you extend that answer session one more hour, it will be useful for us to understand little more better, madam. Because the time is very short. So 2 hours only allotted for stream trim and sim NRA and rump calculations. So 2 hours is not enough. So if you allot 1 more hour, we can learn more things, madam.
Sure, sir. We will keep it in mind. Thank you for your suggestion. Then Monica is saying that this session is really good, really a great opportunity to learn about ion implantation, but there are some signal issues. Yeah, these are always there. So we regret for it. But see, in the time of this pandemic, we just thought that information should always be shared, knowledge should be shared and enhanced. So we, under the chairmanship of our program leader, Dr. Tripathi, we could finally do it. And I hope that people got benefited also. So, of course, there will be always signal issues will always be there on the online portal. So, Aman Rajendra Govindraj is saying learned a lot. Thank you, sir. Then Amandeep Sharma is saying, sir, ma'am, it was nice experience to attend such a wonderful school. Hands-on experience was really good. Please also add some more sessions on hands-on experience in future. So what kind of session you would like to take, you can email the suggestions to us, okay? So we will be trying to put it. So actually this is only on the ion beam interaction with matter, but we actually keep different topics throughout the year for schools, like school on characterization is also scheduled. So suppose if in future we will be having such kind of schools, so we will inform you. Aditi Bisht, thank you for organizing this school. It was really helpful, and thanks to every speaker. Of course, participants are school and speakers are the actually part of any school or event being organized for learning. So thank you for conducting such an informative school. I will also like to thank the material science group for providing support during my experimental work. Okay, thank you. So Balvinder Singh is saying thanks a lot for the knowledgeful experience. Mahendra Rathore, thank you for valuable, interesting sessions and hands-on training. Taranga Dehuri, thank you all the organizers. I think there should be more hands-on training. So sir, you are listening now, so they actually liked your hands-on training a lot. So you need to extend your timing little more next time. So Colin, yeah, please, you are saying something?
Yeah. See, this session maybe is a little short this time, but
Yeah.
you know that you can approach people, and if you have some specific questions, they will be happy to
Yes.
answer.
Yeah, you can always email and say we actually were not having idea that you were able to download. We thought that you have already downloaded the software on your PC. So that is why it was a little bit kept we have kept it very, not that tight, so that you people can always have some relaxed sessions also in between. So we will work upon it. So Vinayak is saying AUC 68 user will be allowed to use the facility. So if it is sanctioned, then you will be able to use it when the corona pandemic is over. Thank you for this helpful session. Thanks a lot. Thanks a lot. This is a big step. Your organization applied the digital advancement to help research students despite this pandemic situation. Of course, thank you so much. Jalad Ma'am is saying well coordinated virtual school organized by IUAC. Thanks to organizer team and all distinguished scientists from abroad. Only one thing participants wants, if they miss anything about that, also has been covering through YouTube. Very successful. Only thing I always want tea and lunch from IUAC canteen, which is always a good quality. Ma'am, we also miss tasty lunch during these kind of events actually. So same here. So the feeling is mutual. Hemant Chaurasia, thank you so much for organizing this school. It was really helpful and thanks to every speaker. Mayur is saying thank you very much to all the speakers. And Dhaneshwar Dake, thanks for conducting such a wonderful. Always, it's a hands-on training was good. Bhim Khan is saying thanks a lot. It will be helpful for new researchers, definitely. So Marshall sir is saying, do you have in India any theorist group who try to simulate the atomic motion under irradiation? So Saf sir, would you like to answer this? Group of theory people who actually do this simulation.
Yes, there are a few groups. I know one from IGCAR, one from IPR, and we had some work. You had done some work here also.
Yes. So Sumit Mukherjee sir and Dr. Saif, they are also doing the same simulation here at IUAC.
Can I add just one small thing? This
Of course.
we have been we have this high performance computing facility. So we have been trying to. This is one area which we have been trying to encourage. And we had last year organized this workshop on this, and this was on trying to use this our high performance computing facility. We start with this MD simulation and trying to go into this what type of thing, this kinematic Monte Carlo KMC calculations on that. So I hope that activity gradually picks up, and we are going to have this next phase of this more powerful. I think how much petaflop? Sorry,
Three.
50 petaflop facility we are going to get into. We are trying to make a user group and start get something on that, so that we can, because this will be one area which can enhance our research output in a big way. So hopefully this will happen, and we will keep in touch with the experts like Professor Tulemon to get their help whenever we go into that direction.
Yeah, thank you, sir. So Devka Mankad is saying interesting session and great opportunity for learning. Kartika Shivagunam. Greetings, Professor. All 5 days were very useful. Myself, being a very new researcher to this field, I learned many new things, and I would like to thank each and everyone for this highly informative session. The hands-on training was so neatly organized. Special kudos to the entire team. So all thanks to Saif sir and Umapati. Umapati, has he joined this session or not?
Indra?
Huh?
I think Marcel sir wants to say something.
Okay. So go ahead, sir, please.
Can I go?
Yeah, please.
Do you hear me?
You want to leave, or you would like to add something?
No. I just want to continue a bit the discussions about theory. What it may be interesting to have computations, but not alone, in collaborations with experimentalists, in order that everybody can understand the difficulty of the experimentalist and the difficulty of a theorist, in order to understand what we are doing.
Okay.
Yes, sir, absolutely. Thank you for your feedback. And now we'll go to the next one. So it is saying, Shiv Kumar P, dear sir, if possible, can you upload hands-on training videos in IUAC YouTube channel? This will be helpful for us. So we will think about it. Thank you so much for valuable and interesting session. Thank you for all organizers, really helpful. So that is all for the feedback session. Any more comments or feedback you people want to give?
Can I request everybody to switch on the camera, so as many people are there, we can try to take a snapshot?
Yeah, please turn on your video for a short while, whoever can. All the participants are requested to turn on their videos.
Even if you are in a car, like somebody was in a car, he quickly switched off, you can leave it on, no problem.
No, sir, it's okay. Why to disturb them? Whoever wish to open their video, please kindly open it so that we can take a screenshot of the participants.
This will tell you, this will remind us how people have been attending this. So in homes, in cars, in labs, in grounds.
Yeah, while walking also, while eating lunch, while taking coffee, tea. So Prachalit is saying, enhanced my thinking, and the school has motivated me towards the research in ion beam. I am very thankful to organizers and speakers. Okay, thank you. Thank you very much for all organizers and all speakers for this school. All sessions are great and very informative. So all are praising our organization skills. So I think we will definitely plan another virtual school soon. It's getting us motivated to do so. Ashokan sir? Dr. Ashokan?
Yeah, if it is planned, yes, we can organize one more, no problem.
Yeah. So Jalaj ma'am is saying that only one more point. Next time, organize virtual school